So is this? What? Wait. What? Does this work now? It says it's picking up audio. Does this work now? Okay, well, that was alright. I don't know what that was. I guess it somehow reset my settings when I was streaming or something. Cool. Alright, that was annoying. Sorry about all that. So, as I said before, the plan is we're doing DP optimizations, and specifically, this is the segment tree and convex hull trick optimizations. And I'm limiting myself to these because there are like just too many of them. And even in a lot of problems, these problems aren't enough to cover all of the broad, like, different types of problems that you can get with this. So I'm limiting myself to just these two for now. And I guess I can change the title too. That's a good idea. Convex hull trick. And spell it out for the new viewers. That's how it works. So let's see. You can find everything relevant in the description. Don't need this anymore. You can find the mashup here and the my other streams here. And actually, I'm going to also include my templates for coding because it's going to be very relevant soon. Now let me answer the questions that have been picked up. Different optimizations. Yeah, I won't be doing those. Those are fancy. I might do them in a future stream, but not right now. Let's see. Roadmap to CP. I do kind of I don't know. Possibly. That might be different from the journey video. I don't know. Is it broken again? Well, it says it's picking stuff up, so hopefully it's not. If I move closer to the mic, does that make it work? It's getting doubled. What? Am I like picking up another device or something? I don't have my phone on. I don't know what's up with that. That might be... Does anyone else have that issue? God, this is so annoying. 8 minutes in and we haven't started anything. ASMR is fine. I mean, that keeps it more interesting than just staring at problems for a long time. Okay, so I'm going to plug it in my Discord because I always do that. If you want to scream if you're using light mode as the tradition, go ahead. Okay. Cool. So here we are on Valentine's Day on Code Forces as always. That's my life. And we're gonna do some DP. So I have prepared these two problems myself, just like on Polygon, to sort of provide an introduction. All right, now let's get into this. I'm gonna need a lot of space today. And what we're gonna do is we're doing two things: segment tree and convex hull trick. So if you don't know what these are, that's fine. And even to make it work, you don't actually need to know what these are. I'm going to describe a technique that many people use at the highest level for complex topics like, for example, FFT and things like that. Because, although this FFT isn't a part of this stream, it's just something people do. Or basically, I think it's called like black boxing or something, where you just like know something. You know enough about something to be able to apply it, but you may not necessarily know how it works internally. And this strategy sometimes works and it sometimes backfires, but with the most basic properties of stuff like segment trees and the convex hull, it's going to work. So here's what I mean. What do you need to know about a segment tree? what we need to do is we need to figure out what this segment tree does. So with a segment tree, it operates on an array. So you have a bunch of indices. And you can query some property of this array. So for example, you can query some property of this array on some range. So I can say I want this range of the array. And then the property I want can be one of many different types of operations. The key is it has to be an associative operation. That means that, like, say you have some operator. I'm going to use this notation for an operator. So you have A operator B. For example, this thing could be XOR, or it could be addition, or it could be the maximum or minimum. There are many possible things we can do. And the only thing that matters about this operator is that it's associative. And what that means is that simply it doesn't matter like which order you do the operations in, you just have to do them all at some point. So basically it means if I move the parentheses around, it doesn't change the answer. That's the idea. And the reason for this does depend on the underlying structure of segment trees, but it's not necessary to know that. So for example, I can use the segment tree to query the maximum on this range, which is often used for dynamic programming. So I can specify that I want the maximum of the elements 2 to 5, and the segment tree will do that in O of log of n, where n is the size of the array. It doesn't have to be maximum, it can be something else. It can be, again, XOR. It could be sum. It could be minimum. It could be a lot of things. In fact, you can even build a segment tree on convex holes, which is interesting. But that's not going to be relevant till later. The other thing you can do other than range query is you can update an index or a range. I don't think these problems require range updates. But I can say, for example, like I can pick some index and I can say that we want to modify it. So we can, for example, set it equal to x, or we can add x to it or something like that. And we can also do that in O of log n. There's also the possibility of range updates. So for example, I can pick a whole range and I can say all of these elements should be equal to x, or add x to all of these elements, or even support both of them at the same time. That's possible. And doing both of them instead of more complex modifications, again, does require an understanding. But the most basic things about segment trees, you're basically able to just like copy pasting code and have a template. And that's most of what I do. I basically just like, my segment tree makes it very easy to do that, which is why I've linked my templates in the description. Here. Yeah, and then with the segment tree, you can just have this update thing, which will update something on a range, and then you could have this query thing, which will query something on a range. Although I will admit my segment tree is not the most beginner friendly, so maybe it's not the best one to use, because I combine it with these things called like types, where if you pass the segment tree a type argument, and then you sort of pass this type into it, and then you can initialize it with something like this. And then this basically tells you to make a segment tree over maximums. And then the update is the range addition. So basically you can add x to a range LR. And in most cases this is enough. Not all cases, but most of them. So yeah, you're welcome to learn how segment tree works. It's eventually definitely a good idea to do that. But for now, it's not necessary. Yeah, sure. If there are other better segment trees that other people have, feel free to talk about those. Okay, so basically, let me find my mouse. So basically two things. We can query a range. For a lot of different things. We can ask for the maximum or the minimum or the sum or XOR or whatever, a lot of different things. Anything that's associative. We can even do like matrices and complex stuff like that, but that's for another day. We're not doing that right now. So we can query this range and we can update element or a range with something like add or multiply or set. And set meaning we can like set all elements to a certain value. Oh, will it let you post the link? I'm not sure if it lets you do that. If it doesn't let you, it might like shadow delete it, so it won't delete it for you, but nobody else will see it. So if not, you can like put a space between the periods or something, and that way it won't actually look like a link. Yeah. So this is what a segment tree does. Care to explain with 2D array? What sort of 2D array? Like a two-dimensional segment tree? Well, segment trees are able to operate on like 1D arrays of size generally like O of 4n, although there's an upper bound based on powers of 2, but using 4n will be guaranteed to work. That's the size you need, or the memory constraint you have. So, alright, fine. I'll give a very brief overview of how segment trees work, I guess. Yeah, I'll definitely have some examples. That's sort of the whole point. Alright, look, I'll give like a 2-minute explanation. There are better ones on the internet. So, here's the idea. We have an array, and we're going to break it into a bunch of ranges. So we can sort of ask about these ranges. So we're going to say this array is a power of 2. So for example, we have 8 elements. So now we're going to cut this range in half, and we're going to make 2 subranges that represent the 2 halves of this current array. So now both of these halves are ranges of size 4. And then we're going to cut both of these in half again, and we're going to represent ranges of half of the orange ranges. And then once again, we're going to cut them in half, and we're going to make ranges of this. And so what this is going to do is, say we ask for some bigger range, for example this, and we're going to query on this range. What we can do is we can ask for, what we can do is, if we know the answers for all of these segments, for example, say we want the maximum. So this segment is going to represent the maximum value of the elements on this segment. And then this is going to represent the maximum value for these. And then this is going to represent the maximum value for all of these elements. And then, so when we ask for this range, instead of going over all the indices and taking the maximum individually, we can use these ranges that we already have to help us. For example, we know the answer for the last 4 elements. So if we take this segment, then we can get rid of all of this, and now we just have this query. And then we figure that out in O of 1 because we already know the answer for this segment. And then now we can reduce the rest of this query to this blue segment, and we can ask for that. And then instead of combining 6 different segments, we only have to combine the answer for 2 of them, and we can take the maximum of the values on the 2 segments. That's the basic idea. I'm not going to explain lazy propagation. It's sort of like more involved. That's like a 2-minute overview of a segment tree. But the most important part here is what it does. You can query a range, and you can update an element or update a range. So actually, I'm going to keep this, because why not? All right, so now before we get into convex hull trick, let's just do the first example problem, because why not? So here's how this problem works. You have a line with n locations. In fact, I'm going to call these islands because I like that. You have a line with n islands, which are sort of disconnected from each other. So imagine these green blobs are islands. And then each location I has some value associated with it. So for example, this would be 1, 2, 3, and 4. Turns out these correspond to both the indices and the values themselves. So all right, now you start at position 1 and you want to jump to some future value. For example, say you want to jump from 2 to 4. You can jump forward from any position to any other position. However, some positions simply won't accept that. So for example, like each island is sort of selective in where you can come from. Each island, for example, this island will only allow you to come from some range of previous islands. So for example, this has the range 2 to 3. So it will only let you come from 2 or 3 to go to this island. You can't come from 1. They'll like just shoot your ship down or something. So you don't want that, right? So the idea is you want to make these jumps to get to a certain island. And each jump has a cost associated with it. So the cost for making a jump is simply the sum of the elements on the range that you take. So if I take this, and then I would take this one. Whoa, what was that? And then I take this jump, then this jump would cost this much, and this jump would cost this much. So there are multiple ways to, oh yeah, okay. And again, you can only jump from a certain place if it's within its range of acceptance. So you cannot make this jump, even though it would give you the lowest answer. It's not possible. Because this 4 only accepts from the range 2 to 3. And in fact, I'll write these numbers next to it. So this accepts 1 to 1, so everything. This accepts 1 to 2, so everything. And this accepts 2 to 3. And every range has at least one element. So with that, you can sort of prove inductively that you can reach any place. Like for example, say you're here, and then if you can reach every place before this, then because this contains at least one of these places, therefore you can make that jump to reach this place. And the base case will be like you can reach 1, and then you want to figure out if you can reach 2, and obviously you can because the range will just be 1, 1. So by induction, sort of, you can reach every possible location. But that's sort of less relevant to figuring this out. So n is 200,000, but let's ignore that for now. Let's just say we wanted an O of n squared, like basic dp solution. So we can say something like, let dp of I be the minimum cost. Actually, I should write these values in. 1, 1, 1, 2, 2, 3. Let dp of I be the minimum cost to get to I. To get to location I. So dp of 0 is simply 0. Or dp of, yeah, I'm using 0 indexing. So dp of 0 is equal to 0. And then let's say, for example, what is dp3? Well, to get to dp3, or to get to location 3, which has the value of 4. Again, I'm using 0 indexing here. It might be a bit confusing. But to get to index 3, we can come from 2 possible locations. We can either come from 2 or we can come from 3. We can come from any location on this range, meaning that the cost to get to this one is, if we select some previous value we're going to, it's going to be the cost to get to this one plus the cost of this jump. So the cost to get to this one is dp1, and then the cost of this jump is the sum from 2 to 4. And I had this function Sij, which is simply the sum of all elements between I and j. So using that function, we can say this cost is S of 2, 4, which is the sum of, or S of 1, 3, which is the sum of elements between indices 1 and 3. Oh yeah, we're doing the first one. I should do that. Right, sorry. Now I can pin this. Alright, actually no, that's a bad link. Hang on, let me try that again. Because if you aren't invited to the mashup, that link won't work. I'll just do that. That will work, and then pin that. Okay. That should work. Okay. So dp of I is the minimum cost to get to I. And then to get to, for example, 3, we can come from any location that works for its range. So in this case, we can either come from 2 or 3. So it's the minimum of, or we can either come from, I'm going to write out the indices now because I'm confusing myself. So this is index 0, this is index 1, index 2, and index 3. So here we can come from 1 and then jump from 1 to 3. So it's dp of 1 plus s of 1, 3. Or we can come from 2 and get dp of 2 plus s of 2, 3. And in general, for the general case, where each value has a value L and a value R, like for example, this is L3 and this is R3, the ranges, then it's the minimum so the general dp of I is the minimum over all values within its range. It says you can't join. Yeah, don't use that link. Use this one in the description because that's an invitation link. Ignore this message, actually. I'm going to remove that. So for this dp value, we pick some previous index to come from. And we can pick any index that's within the values of this range. And in fact, we want to try all of them. So we pick some index, and then the cost to get to that index, the index j, is dp of j plus the cost of jumping from j to I, which is, so if we're jumping from j to I, then the cost is the sum from j to I. So the sum of all elements in that range that we jump from, that we jump through. So this gives us an n squared recurrence. And now we want to optimize it, which is sort of the whole point. The current problem, you can see the description that will take you to a mashup, and then you'll have a list of problems on that. Or it'll take you to like a contest. So notice that we're asking for a range. But the problem is that this formula is kind of annoying. And there are 2 ways to do this. There's a smart way that involves like looking at how the prefix sum works and then realizing that some elements are counted twice and some are only counted once. But I'm not going to do that. I'm going to do the more involved way so we can get some practice with it. So this is kind of annoying because it's a formula that depends on both j and I. So if we were to wrap some stuff in a segment tree, for example, it wouldn't work. What we really want to do is we want to build a minimum segment tree, and then we want to use the segment tree to query the minimum value on this range from L to R, which is, again, that's sort of the whole point of a segment tree. It lets you query something on a range. So you can query the minimum on some range. And then we can update the segment tree to set the value of dpi so that in our future, like when we get to a future value and we want to jump from dpi to somewhere else or from I to somewhere else, we can query the segment tree involving I. But the point is we want to build a segment tree so that we can query these values. But this sum is annoying. Let's convert it to something else. One way to do that is to use prefix sums. Wait, does the mashup link not work? Should work theoretically. If you're not logged in, it might not work, but I don't know why it wouldn't. Okay, but anyway, we're going to optimize this using prefix sums. So the prefix sum of I, let it be p of I, equals simply the sum of elements from 1 to I. So if we take some range, then this would be, or actually no, this should be 0 to I, because I'm using 0 indexing and being annoying about it. This would be this. And then yeah, so then this would be the sum of these 4 elements, the sum of indices 0 to 3, would be P of 3. And then we do that for all possible values. And then, like, say we wanted the sum from say we wanted the sum from sum A to sum B. So we can make this whole array. And then we can ask for the prefix sum of B, so that this is the range 1 to B. And then this gives us the elements 1 to B. And then what we can do is we can subtract out the prefix sum from A minus 1. And notice that when we get rid of this, then the thing we're left with is the range from A to B. Because we took everything less than B and we just subtracted out everything that's less than A minus 1 because that's outside the range. And that gives us exactly the range we want. So, cross these out because I'm too lazy to erase. And then the answer that gives us for S of A and B is equal to the prefix sum of B minus the prefix sum of A minus 1. We take everything and we simply exclude everything that's not within our range. So if we do this instead, now we can do something better. We can have this be dp of j, right? Plus prefix sum of I minus prefix sum of j minus 1. Now notice that this minimum only depends on j, meaning that I is constant when we're iterating over j. So what we can do is we can take out this, because this doesn't depend on j at all. So this can be the prefix sum of I, and then now we're evaluating this minimum for that. Now both of these depend on j only. Meaning that, like, in a segment tree, say we want to query this range, like for example the elements 1, 2, and 3, then we could literally just stick this in. And then we can use the segment tree to get the minimum value of these values and then add pi to it at the end. So the segment tree will let us minimize this. And so here we would literally just stick this in. We would stick in as the values of the segment tree dp of 1 plus the prefix sum of 0. And then here we would stick in dp of 2 plus the prefix sum of 1. And then here we'd do that. And then we can just query the minimum on these values. And then that's just this recurrent. And then that's just whatever this formula is. So the key thing I did here is we had this formula that depended on both I and j. And then we separate it. Oh yeah, sorry, that's minus, you're right. My bad. But the point still stands. We want the minimum of whatever this is. We want the minimum of these. And the key idea is that we separated I and j. Everything that depends on I can be sort of like completely independent of finding this minimum, because this minimum is what's taking up the complexity. So everything that's constant based on I can be brought out because it doesn't depend on it. No matter what j is, this is going to be the same. So we isolate I from j, and then everything else only depends on j, meaning that we can stick it in the segment tree just as this formula, because this just gives us like, it's just everything. For a given j, we want to find the minimum of these values. So we're going to stick these values into the segment tree, and then that gives us Like that just lets us query the minimum of this. So we would do this for everything. And then we just, for convention, let the prefix sum of -1 be 0, because it's the prefix sum of no elements, so that's fine. dp of 4 minus prefix of 3, and then dp of 5 minus prefix of 4. And then at any point, we can just query the segment tree for whatever range we need. And that lets us optimize this recurrence. So yeah, I'll put this in code next. Alright, so first I'm going to paste in my segment tree. And I have the preset values for maximum, minimum, and sum. Everything else sort of takes a bit of modification, but these are the most basic ones. So the way this works is you simply copy paste in both of these. You copy paste in the segment tree and then the type you want, and then we declare a segment tree using this type as a template argument, like so. And again, you can find these in the description. Oh, hi Gabe, what's up? So yeah, let's do some stuff. I also realized I should update the subscriber count because I always do that. So if you want to be part of that, there's a certain button that you're always able to push at any point. You know what it is. I'll leave it at that. Yeah, so let's see. We have a value n. We're going to read that in. We're going to read in the values of the array. And then we're going to read in the values li and ri. And n is up to 200,005. Hopefully I would know. I wrote the problem. And I'm going to use zero indexing because I like that. What if AI is 118 instead of 126? That would overflow. So it's not so nice. I mean, you can use like something like int128 or Python, but it would just overflow. So it's not a nice thing. Maybe even string comparison addition, if you like doing that to yourself. So we can also compute the prefix sums. Oh wait, this should be range. Confusing this with my other code. And the way I do prefix sums is I simply keep a running sum. So like, if we're doing prefix sums here, I would start the sum at 0, and then say this is like 2, 3, 7, 5, 9. Then to this running sum, I would add this element. And then now this represents the sum of the first 1 elements. So this is just the prefix sum here. So this prefix sum gets set to 2. And then I add 3 to this running sum, and then this prefix sum gets set to 5, because now this is the first 2, and then etc. So that's how that'll work, and we're going to do that now. And then now we're going to make the segment tree work. So the way you initialize the segment tree is you like pass it a value n and then some array, and then it'll initialize it to like work with that array. So I'm setting everything to 1E18 because that's necessary. That's how the query works. So this segment tree is sort of like representing the DP values, where it's like, yeah. So actually I'm going to do this. DP of that, DP of that, DP of that, DP of that. And then now what we're going to do is we start filling in these values. So actually first we want to insert the initial value. So it's, yeah, and actually this comes out to 0 because dp0 is always 0. So that's fine. We've already inserted the initial value. And then the next move is to work with 1. So to figure out 1, we just plug in this recurrence. So we're going to simply query the segment tree over the range LI, RI. And because we already put these specific values in the segment tree, so we don't have to do any more work. We just have to add the prefix sum of I to it. So we query the segment tree for range I. Actually, I'll use better things. More clear variable names, I guess. And then 1 indexing, or 0 indexing. So this is the left value of I, and then the RV of I. And then dot value, because you want to extract the value, so you just do that. In fact, this is it. This is DPI. So the reason I set these to a big value like 10 to the 18th is because we're doing a minimum query. So if some value is uninitialized, we don't want to... Wait, is that even relevant? I don't think it is, actually. Yeah, I don't think it is, because in some cases we would want to do this, but in this case specifically, every value is going to be filled in. So there's no like unfilled in values, because if some value is unfilled in, we want to set it to something huge so we don't ever consider it. But in this case, that's not even actually necessary. So, sure. And then, so this is DPI, that's it. That's just, we just plugged in the formula. When we figure out the formula on paper or in Paint, that's just it. And then to update the segment tree, we simply set the value of the current index to the value that we want. We want to insert the value dp of I plus p of I minus 1. So we at the index I, because this is a range, we have to specify that we want between I and I. We're going to update it to be dp of I minus p of I minus 1. And that should be it, hopefully. Had some troubles with my system running out of memory so that I literally can't compile files. I don't know what's up with that, but I hope that doesn't come back. So we test this on the samples, which I've intentionally made strong to be nice to you. Ta-da, it works. Is this visible? Yes, I'm going to try to cover the hard problems. We'll see how far we get. I'm not sure how long this is going to last. But as we get farther, I'm going to sort of like rush it a bit more, because it's going to be kind of the same thing repeated a lot. Okay. But anyway, the introduction is going to be the longest part, I think. So we just did segment tree. And by the way, as you can see, I have solved some of these before, which is fine. The whole point of this is just to like go over them. So now we get to convex hull trick. And, yeesh, this is a mess. Yeah. So now we get to convex hull trick. And once again, I'm going to go over a brief overview of what we do with it, and then like a very brief description of the way it works. But it's not necessary to understand how it works, especially with this one. All we really need is what we can do with it. So convex hull trick will do some things for us. Right, so we're gonna do that. Whoa, that's a mess. Right, so it lets us do two things. One, Actually, what a convex hull trick is it's sort of a set of lines. There are multiple ways to do this. There's this thing called a Lee Chow tree, which I'm not going to use, and then there's just this thing called like dynamic convex hull, which is where it gets its name of convex hull, and I will explain all of that shortly. So it's a set of lines, basically. Like literal lines, like lines on a 2D coordinate plane. Like I'm going to insert a bunch of lines, for example, like this, and then like this, and then just draw a bunch of them. Is that a good drawing? No, not really. Let me make something more clear. Okay, why did I draw the line before the... Okay, so say we want something like this, and something like this, and then potentially something like this, and then something like this maybe. So we have 4 lines. Imagine this is like upright. Like imagine this is a normal XY plane that isn't slanted for some reason because I can't draw. So what we want to do is, we want to do 2 things. We want to insert a line. At the most basic level. And we want to pick some point X. And at this point X, we want to figure out the highest line at that point, or the value of the highest line at that point X. So for example, each line will evaluate to some point because it's an equation. We have like f of x. The standard equation is mx plus b, where m is the slope and b is the intercept. So like, for example, this line would be something like, say the slope is like -1/10, and then this intercept is -5, then this line would be -1/10 x minus 5. You guys know how line works, right? You guys know how lines work, right? Hopefully. So that's the basic idea. And yeah, so we're evaluating the line. We're evaluating each line at a certain x coordinate, and we want to figure out the maximum value we get from a line. So it's just like the highest point at a certain x value. Damn it. Okay. All right, I can't get rid of everything. So I'll just leave this on. Okay, I guess not either. I don't know what's up with that, but yeah. So basically we're querying an x. We're asking for the highest line at x. How is this relevant to DP? Well, it turns out there are a lot of recurrences that can be optimized like this. Like, for example, consider the very basic problem. Like here, once again, we have jumping. And you can jump from any position to any other position. Like, say we have A1 or A0, A1, A2, A3, A4. This is not the second sample problem. The second sample problem also involves prefix sums, but the idea is you can jump from any position to any later position for a cost of AI times AJ. You can jump from I to J where I is less than J, and then the cost is this. Then you, once again, let DPI be the minimum cost to get to I. And then the recurrence is DPI equals the minimum over all j that are less than I. So like all previous positions. Say we're getting here, then this would be the minimum of these previous 3 values of dp of j plus the cost, ai times aj. Notice that this is constant relative to I. So if we had all of these j values in some data structure, look at this. This is a constant. This would be the value of the intercept. This is a value that's being multiplied by AI, so this is the slope. And this is some constant that we're plugging in that we're multiplying with some other value in the data structure. This would be the value of x because this is what we're looking for. Out of all these lines where the intercept is dp of j and the slope is aj, we want the highest, or actually wait. So technically the convex Hull trick gives us the highest, and that's the way it works. But if you want the lowest, you can just like insert the negative slope and the negative intercept, and it would just make everything negative. So it would query the least negative point, which would be, if you flip it again, the smallest point. So if you negativize everything, it gives you minimum instead of maximum, and then you re-negativize it like when you're done. So we're asking for the lowest point at a particular x, ai, of these lines. We just have this form here. So that's the idea. To use convex Hull trick, we can convert some recurrences to this formula, or this type of formula. So we insert a line, specifically a pair of m and b, where this is slope and this is intercept, and we can query x and get the highest line at x. And the way this works, the reason it's called convex Hull trick is because it sort of maintains the lower convex hull of these lines, and it does so by eliminating useless lines. So for example, look at this line. It's up until here, it's always going to be under this red line, meaning that on this side of the x-plane, it's entirely useless. And on the rest of the x-plane, on this side, it's going to be under this orange line and this green line. So like this cyan line is totally useless, and that means we can remove it. And that's why it's useful. Because when we remove all of the obsolete lines, we get a structure that looks like this. We get sort of this like hull-looking thing. And then what we're interested in is this. In fact, this green is sort of useless too. But we get this hull-looking thing, and the point is, as we go further to the right, the slopes start increasing. And then to figure out the line that we're interested in, we just figure out whatever line is on top at that point. And we can sort of maintain for each interval, I guess. I'm not entirely sure how the implementation works, to be honest, but we can maintain for each interval sort of like the interval that it dominates. Like this line will dominate to negative infinity, this will dominate to positive infinity, and this orange line will dominate at this range, and this cyan line will dominate in this range. And then we can use binary search to figure out the line that's currently dominant at our current x. I think that's the idea. I'm not entirely sure, but that's one way it would work. Seems a bit involved to do so. But that's the way convex Hull trick works. So now, in the context of this problem, let's figure out what we need to do. It's very similar. In fact, it's very similar to this one that we just did. Except the cost is not ai times ij. It's the sum from I to j times some other value b sub j. So we also have values b0, b1, b2, b3, and b4. And so now the cost is going to be the sum from I to j, just the sum of values from the beginning to the end, times the value of b at j. So once again, we want to try and convert this into a line somehow. How do we do this? So we have S of ij times bj. So let's expand this recurrence out of it. We get the minimum of all j less than I. And again, like I said, I got rid of the values L and R because I'm not mean enough to make you write a segment tree over convex hulls. But the last problem, spoiler alert, may involve that, maybe. So have fun with that. But for right now, we're simply interested in the basics. So this is dpj, and then we're going to use prefix sums once again. So it's the prefix sum Actually, sorry, this should be the sum from j to I, because j is less than I. Not the most important, but it's something. So the prefix sum of I minus the prefix sum of j minus 1 times b sub j. Let's expand this out a bit more. Minimum from j being less than I of dpj plus p of I times bj minus p of j minus 1 times bj. Now let's sort of just like label these values. This is a value that depends on j. This is a value that depends on j. This is a value that depends entirely on j. And this is a value that depends on I. Or actually, wait. Both of these values depend only on j. And this is a value that depends on I. So with respect to I, whatever this is constant. So if we were to represent this as a line, these orange values could represent our intercept, our value of b, the constant. And then this is a value that depends on I, so with respect to j, it's constant, and this is a value that depends on j. So if we're querying the minimum value of this, this would be our value of x, and this would be our value of the slope. So if we separate these slightly more, we get bj times, or the minimum over that of bj times the prefix sum of I plus this constant value dp of j minus pj minus 1 times bj. All just messing with the formula. So this is m, this is x, and this is b. Because again, we're asking for a particular I, what's the maximum value of this recurrence? So that's how this works. And then like to do the code, we literally just do it. Like we have the formula already, we're just plugging it in at this point. So the idea is as we sweep from, sort of similar to the prefix sums, as we sweep from like 0 to m minus 1, we like maintain the set of lines that represent our current prefix, and then when we get to this one, we add this line in and then move to the next one, and then we can make these queries simply. So let's do that. And my template also has this. You can go to util files and then go to concepts, and then you'll have convex held dp here. And then this is sort of a version I adapted, but it's basically just copy pasted because I don't want to code this myself. So that's the idea. You can copy paste this in, and then it will handle the convex hull stuff for you. So you would do this as something like, so we can get rid of LV and RV, and then we would do something like dynamic hull, called like CHT or something. And then in our convex hull trick, we're going to insert this initial line. So the line we have, the lines we're going to insert are m is bj, and then the other value is dp of j plus p of j minus 1 times bj. This is the line. For 0, this is simply, this is 0, this is 0, so it's all 0. Actually, wait. I think I confused myself. I think it's slightly backwards actually. Like this should be I instead, and this should be I, but it's sort of the same thing, right? Like if we, yeah, it doesn't really matter. The whole point is we still get. Okay, yeah, I kind of messed this up. 1 second. Let me fix this. Yeah, okay. Because it depends on I, and we're going from j to I. Yeah, this is what I get for like swapping my own indices. I get stuff like this. So we're interested in bi. So this whole thing should be bi, and this should also be bi. So that is my mistake. We get dp of j plus pi times bi minus, I knew this seemed wrong. I knew this seemed wrong somehow. I just, like, I didn't know, it didn't register. Yeah. So now we can note that this depends entirely on I, meaning that we can, like, this is iterating over J to figure out what the best J is. But no matter what J is, this part's going to be constant, meaning we can take it out of this sort of minimum equation. So we want Pi times B of I. I don't know why I did that. That's even weirder. That's what you get when you sleep at 2 a.m. and then do a morning stream. And then, so this is plus minimum J being less than I of negative P J minus 1 times Bi plus dP of J. Yeah, sorry. I think this should be what it is. And then this is the value of the slope. This is the constant, and then this is the x because it depends on I. Yeah, okay. Sure. I knew something didn't make sense because this should have been 0 initially. So at the beginning, this is, so we insert the line at the beginning with the slope of 0 and the intercept of 0, because these are both 0 for the first index. And then we're going to put stuff in. So dP of I is P of I times B of I. And then again, because convex Hull trick gives us the maximum, what we're actually going to do is insert the negative slope and the negative value, and then take the negative of that at the end. So that we can, for example, the slope we would insert would actually be P of J minus 1. And then we would insert negative dP of J, and then take the negative of whatever this is. And yes, this video will be available after the stream is over. It'll just be on my YouTube channel. Like it'll just say like the previous topic streams, you can find them all in the videos list. So this would be minus because we're negativizing it. And then we evaluate at the point B of I. Then the line we insert is simply this. So the slope is P of J minus 1, P of I minus 1. And then this is negative dP of I. That should be it. Notice how simple this for loop is. I don't have those anymore. Because if we do all the work on paper, it's sort of like a trade-off. Then the code's so simple. Like you just plug into formulas that you already had. 6, 18, 40. Have some bigger values here. Negative 32, negative 132, negative 142. Yep. And yep, looks good. I love myself for making strong samples. Ta-da, it works. All right. Not biased at all because I wrote the problems. Anyway, so yeah, this is how we do this. Feel free to, if you want, try and derive these formulas by yourself instead of looking at these, because it could help to just figure out the way to do the manipulation. We're going to be doing a lot more manipulation in the future problems, especially in the later convex hull ones, for example, these. And this one especially. This one's really fun. But that's sort of the bulk of it. Yeah, sure, I can go over the code. Oh, the code for convex Hull trick? I don't actually know how this works, kind of. It's sort of like it's sort of a magical oracle even to me, because it's just like, I mean, I know the basic idea behind the way it works, but I don't actually know the way the implementation is done. But assuming the convex Hull trick is a maximum oracle, is like a magic oracle that just gives us the minimum the maximum for these lines, like assuming it does what we say it does, then the rest of the code is simple. We just read in the values, take the prefix sums, and I explained how I did that before at the end of the segment tree problem. Do the DP, and then we just implement this formula. Like this is just a single query to the convex hull, and this is that. And then this line we insert is just going to be these values. That's the idea. And then the segment tree is similar. Like we just implement a formula, and you can rewind if you want to like see the formula for the segment tree one. But again, you can find this code at my templates in the description, and this is all here. And you can go to something like concepts, for example, and then this will give you the convex hull one, or templates, and then segment tree. I might make a tutorial on my segment tree later. Would you guys want that, just to like figure out how this works and then maybe do another example of a better operation or something? I could do that if you guys want. I don't know. Not right now, but potentially later. Anyway. So we can get into the third problem now. And for some reason, it always, no matter what, it always forces me to scroll down. By the way, we're still in code forces, right? Yeah, okay. No matter what, it always forces me to scroll down. I don't know why. It's so annoying, because whenever I wanted to verify that these links actually work, like I don't know. Pet peeves. Yeah, so this is the plan. Oh, I realized I didn't even update the problem. My convex hull trick, maybe, possibly. Again, not right now. I'll see if I even understand it later. But, let's see if we do that. And then I'll pin that one instead. Yeah. Remind me to do this after every problem, because otherwise I'm going to forget. Did that just not work? Okay, it worked. Okay, there we go. How hard is the theme? Well, I don't think there's any particular lower bound rating. It's sort of involved to figure out the way the formulas work, but if you understand like basic algebraic manipulations and stuff like that, all of this is sort of simple. It's just we're working with magic here, kind of. We're saying a segment tree is a magic like it's a magic, how do I say it? It's a magic box that just does a certain thing. And then we don't care about how it does that thing. We're saying it does that thing in a certain amount of time and we're done. Oh yeah, by the way, and obviously like the convex hull trick works in O of log n, because it's if it was O of n, that'd be stupid. The convex hull does both of its things in O of log n. The template link, you can find it here. Actually, adding it in code would not be a bad idea, sure. Okay, I'll just do that. Yeah, it is a black box. Oh, the exact file link? I'll just like send that. I mean, the convex hull is that. I mean, doing that for everything is kind of annoying, especially when I'm doing things in contests. But like, you can find things. They're pretty easy to find. Like, I called everything what you would expect it to be, like seg tree. Stuff like that. It's not that hard to just like search for it. Okay, anyway. Here we go. Subsequences. For the given sequence with n different elements, find the number of increasing subsequences with k plus 1 elements. It is guaranteed that the answer is not greater than 8 times 10 to the 18th. Okay. So k is at most 10. And then AI is up to n. That's important. So we're going to define a basic thing. There are multiple convex hull files? Wait, what? Where? I thought there was only... I mean, there's this... And then ignore these links. You can just copy this code directly. Oh, this is like a convex hull itself. There's a convex hull, and then there's this convex hull trick which uses it specifically for this DP thing. But this in itself is just like the basic convex hull, not the DP optimization. They're different things, sort of. So basically we have this array. Let's say, for example, we have 1, 2, 3, 5, and 4. And we have some value k. And we want to figure out the number of increasing subsequences. So like subsequences where like some subset of elements where every next element is greater than the previous one of length k plus 1. That's it. So define dp of I and j to be the number of subsequences of length j ending at I. Copying is not bad. I will make a video on that later. I'm going to argue this until the day I die, but copying blindly is not bad, provided that you understand what you're doing. You don't have to understand the code, you just have to understand what it's doing. And I will argue this. And I do this all the time too. Like it's not like this is normal. I don't understand to be perfectly honest, I don't understand this code, but I've used it to solve basically all of these problems before. Yes, have a strong template, then just do things. Okay. Oh, I have tea, which is sort of supposed to help with my cough. I don't know how good of a job it does, but it's sort of working. So we have subsequences, that's an ugly Q. We have subsequences of length j ending at I. And then, so say we're like here, and we want the third element in the subsequence. Meaning that we have to extend some previous subsequence that was at its that had 2 elements. Like say we want, for example, 2 previous elements. Yeah, I am having honey tea, so it sometimes works. It's not that effective, but it sometimes works. So say for example we want the previous 2 elements, and then this is going to be our third one, so we want to extend some subsequence of length 2. And also we can only extend a subsequence where this element is greater than the last one. So yeah, so the way this transition will work will be so dp of I and 1 is equal to simply 1, because this is the transition of starting a new subsequence here. We don't extend any previous one, so there's only one way to do that. And then dp of I and j, where j is greater than 1, is going to be, again, say we're at length j, then we're going to extend some subsequence in this range of length j minus 1. And we're going to only be able to extend a subsequence that has a previous value. So this will be the sum, because we want the number of subsequences, of dp of k, where k, again, is some previous element that we're going to extend the subsequence from, and j minus 1. Ugly cough, yeah. Where k is less than I, because k must be less than I because, like, we want to do that. Like, we're only extending from the previous elements. And also, the array value must be less. A sub k must be less than a sub I, because we can only extend from a previous value. And this is it. So, over all previous indices, of the ones we can extend from, meaning that we have the index being less and the array value being less, we're going to include that value in our sum. So this is n squared k, which is not nice, but we can optimize this. Assume we're iterating in this order, meaning that automatically k being less than I is satisfied, because we're just going to totally ignore the rest of this. We're going to iterate from left to right. So now we really want the sum where ak is less than ai. Now, how do we do that? And the answer is with a segment tree. We want every value, we want the sum of this dp value for every value where its array value is less than I. All of them. So for example, we can consider it being on a range from 1 to ai minus 1. We want the value of dp of something and j minus 1 over all values where ak is in this range. Interesting, interesting. And as we noted earlier, the array values are up to n. That's kind of convenient, because we can build a segment tree on these array values, right? So that's it. We sort of flip it. So instead of building a segment tree on the instead of building a segment tree on the indices, we build them on the values. And then for a given AI, we can query the sum over all values that are less than that. So we build a segment tree. This will represent, for example, the value 0, the value 1, the value 2, the value 3, the value 4. And then say we come across the value 3. So then this gives us one way to do it of length 1. So at length 1, we would simply add 1 here, because we have one way to do it. And say we encounter the value 2. So the number of ways to extend it to a sequence of length 2 would be this, because we can extend any value between 0 and 1. These are all 0, so it's nothing. But we do still have one way to do it for length 1. And then, so this is like length 1, length 2. This is not the best way of doing this, but again, now we have something here, and then like say we built a sort of like another segment tree over the next j, because we want to do it over all j, then we get 0. And then here we're going to, for 4, the number of ways to extend a sequence of length 1 to make length 2 is this, every value that's less than it. So we just query this previous value, and we get 2 ways to do it of length 2. We have no ways of doing it of length 3, because we have no sequences of length 2 at all. And of course, we still have one way to do length 2. And yeah, so we build k plus 1 segment trees, or we build k segment trees, each one representing like these values for a specific length. And then we can query all values less than a certain value on the segment tree and make the sum of it. And okay, so when I get to OI and I can't template, I'll be sad. Yes, that is true, but I don't think I'll get to OI, because I mean, Yusuko, there's Yusuko, but that's like, it's often simple enough that I don't get to the point of needing a template, because I don't solve the problems. So I don't need templates if I don't write any code, if I don't solve anything. So, you know. And then getting past Yusuko, I don't know how that's going to be. It's going to be unlikely. See how it goes, though. But the point is, we're just optimizing this transition with a... Yeah, I mean, Yusuko is an OI, but, like, I told you, I don't solve anything, so there's no code I have to write. You know? Like, the hardest thing I solved was, like, ternary search last Yusuko. And that was it. And ternary search isn't even a template, so, you know. Okay, anyway, I'm gonna get into the code of this. Maybe this will make more sense if this explanation doesn't. C into n to k. I'm also gonna make it so we make the values between 0 and n-1, just to 0 index once again. Because I like 0 indexing. And then, yeah, so now we're going to make segment trees again. Except this time we want sum, so we would go to my templates or however you do it, and then we can use a sum segment tree, and that would be cool. Yeah, that's not what I'm saying. I'm saying I don't get to the point of writing templates. I don't get to the point of needing templates so that I would have to write things out. st10. We're going to make it of size 10, and then just set some fill array to 0. sti.init with an array of size n and the blank array of b. Now, for I equals 0, I is less than n, I plus plus. Then we're going to set some j to, we're going to fix some j and iterate over that. Alright, now this should be up to k. And I'm using 0 instead of 1 because I'm just, like, lazy. So actually, dp of I and then 0 is equal to 1. So this is sort of saying we're extending a sequence of length 0. Actually, you know what? I'm going to not be confusing. We'll just let this actually represent like what it represents. So dpi of a sequence of length 1 is 1. Then we iterate from 2 to k, and this is the new sequence we can have. Then this is simply asking dp of ij is equal to the sum query stj minus 1 dot query. Because again, we're fixing j minus 1 and we're building a segment tree over this length. And then we're doing that for all possible lengths because there are only 10 of them. And then we query every value between 0 and ai minus 1. Well, actually, dpij is equal to 0. Then if there are values to extend at all, if ai is greater than 0, because otherwise we would get negative and that's bad, then that's that. Then we update stj.update, and we're simply going to add these values, the dp values. So the index I, the index AI again. So we update from AI to AI and then add the value of dpij. That way in future values we can just ask this sum query again. And then the answer, this is sort of hacky, but the answer is just like the sum of all dp of I and k. So actually, let's just do that instead of being hacky. Theoretically, we can do a segment tree call at the kth one and then do that, but it's not necessary. So actually, I don't need to go up to k here. Like, the answer is just, for each element, how many subsequences end at that and have length k. That's the idea. And this should be dot value. Forget my own template. Nine. Okay, that's fun. Let's see. All right, figure that out. So if we use the same template with other people, will you be found on Codeforces? I don't think so, as long as the code itself is unique. Like, I'm sure other people have used my segment tree in the past and not had problems with it. It may generally be a good idea to write your own, but I mean, I've never had problems, and this has been publicly available to thousands for a long time, so I don't know. I think like detected for plagiarism or something. I would assume that's what it means. Alright, wait, so what's with this? Do we increase k? I don't know why they want k plus 1. Actually, this should be 12 then, 12. I don't know what's the point of just not making it k. Yeah, okay, there we go. So that's it. We just stick this recurrence in a segment tree and do some stuff. And the answer is not greater than 8 times 10 to the 8th, so hopefully this works. Seems like it would. We don't go out of bounds or anything. Test 29. There we go. That was 1 second. You know what? I think this is sort of tight, especially for other wait, shoot, that's not what I meant. For other languages, this is sort of tight, so I'm just gonna like cheat a little bit and make this higher. Just for the sake of this problem not being annoying. So yeah, I'll be nice. Let's see, has anyone gotten time limit exceeded on C? I guess maybe it's not a problem, but if you have a dumb segment tree template like me and then have some trouble with it, I don't know. Depends on things. Okay, now we move on to D, and so I can just do that, and then pin. Oh yeah, I heard there's some like contest going on like right now or something. Where is this? Wait, hang on. I wanna find this. Is this now or is this not now? Like, I know there's this, and this sort of exists. It's called CodeRams, and I was involved in testing it, so it's kind of cool. I don't know what's up with that, but you can check out this blog in recent actions if you want. Supposedly that's starting in 2 minutes. So if you're interested in doing that or just some other contest, like, this video will be available on YouTube, so it's not necessary to be here right now. Although it's kind of nice to have more viewers. Who knows? Up to you guys. I pinned that, right? Yeah, okay. So we have this we have this problem called Hanoi Factory, which is based on the towers of Hanoi, or the yeah. Okay, so I have read this, so I don't need to. Like I said, I've sort of pre-screened all these problems. There's one that I've sort of had trouble with. I'm actually still not sure how to do it, which is interesting. But that was at 2 a.m., so it's not 2 a.m. now, so hopefully I'll be able to do it. But here we have a bunch of rings. We have a bunch of rings. How does this work? Yeah, so we have okay, I'm trying to figure out a good way to draw this without it like being really annoying. I guess I can just draw rings, yeah. So we have rings. Whoa, that's too far. We have rings which are sort of like this. And then they have like an inner radius, R1, and then like an outer radius, which is R2. Or specifically A and B, I guess. So this is like, this would be AI, and this would be BI. And these rings also have some sort of height. I drew myself into a corner here. Guess I can try this, and then how'd you do this? How do you draw with depth? I'm not good at this. Guess we can do something like that. That looks terrible. Alright, I'm not good at drawing, but the basic idea is that these rings have depth. No, it sort of like blends in, doesn't it? Alright, I'm gonna stop trying before this gets worse. But the point is these rings have depth. Or, yeah, so they have heights, which are H of I. And so we're gonna stack these rings on top of each other. And the way we can stack these rings is sort of like, we have some conditions. First, like consider consider we stack rings on top of each other. So first, the like the outer radius of the rings must get smaller as you go higher, or they must like be non-decreasing. So if we fix some rings in some order, for example, then we must have that the outer radiuses are non-decreasing. So like B1 must be less than or equal to B2, less than or equal to B3, less than or equal to B4, etc. And then we have that the rings also should not fall inside each other, sort of, which means if we have a really small ring here, then it's not going to even be on top of this ring. It's going to just fall inside it. So what that means is that for every ring, like rings adjacent to each other, the outer radius of the higher ring must be greater than the inner radius of the lower ring. Otherwise, it would fall inside it. So try and like visualize that, sort of. Like if we have this other ring here, where this is the outer radius. If the outer radius is smaller than the inner radius of this one, then it would fall inside. So the outer radius of this one has to lie between these values. So that's the idea. So for example, we must have that A1 is strictly greater than B2, and A2 is strictly greater than B3, and A3 is strictly greater than B4. That's how it works, right? Or is it the other way? No, wait, yeah, it is the other way. Whoops. Yeah, sorry. So B1 must be strictly greater than A2. Yeah. That makes sense. B2 must be strictly greater than A3. B3 must be strictly greater than A4. Yeah, I do try and do these streams somewhat often, but yeah, it's been a while just because of like a lot of things happening at a lot of times. Hopefully they should be occurring more frequently soon. I say that with hope. It's not a guarantee, but it's hope. Same amount of hope that I've had for the past few months. Okay, the more I draw on this, the uglier it gets. So, yeah. And then also we want to maximize the sum of the heights. So the idea is we want to get rid of one of these conditions at least. So let's get rid of this one. And this is nice because it like say we just, how's this going to work? We're going to build the sequences in an order that like automatically satisfies this. So let's say we build them from largest to smallest. Then when we put some ring here and we have some other ring here, and we're going to like put this one on top of whatever the one this one is on top of, or we're going to put this one on top of this one. So like this, actually this would be here, and then we'll put this on top of this ring. And I don't know why I'm drawing squares, because squares are easier to draw than circles. But that automatically satisfies this, because we're putting them down like in order. And actually, I guess, okay, I'm sort of messing up the order here, but the point is like Yeah, this is not great. But the point is like the 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 outer radii have to be non-decreasing as you get higher, and also like the rings have to not fall into each other. That's the point. I think I've messed up the ordering a bit, but that's, you know, it's fine. So then also we must have that. So let's have this recurrence. DPI is tallest tower with I being the top. Because notice if we have a tower where I is the top, then we don't care about any of the rings that are under it. We only care about I, and we want to satisfy the new condition sticking something on top of I. We don't care about the other rings because they're all irrelevant. The only thing that we care about for the constraints are I. So to compute DPI, is, so it would be HI because you can stick HI on top of it, plus the maximum of some other tower you can stick it on top of. So what are the conditions for sticking some tower on top of it? Well, first, say we sort the towers in descending order, like this, or sticking this on top of some other tower. So first J, the index J we use must be less than I, because we're doing this condition. And then we also have that this tower must not fall inside. So that means that BI, the outer radius of I, must be strictly greater than the inner radius of the thing we take. And then this is dp of J, I think, right? I hope. Notice again that if we iterate through all of these, why did they make it 10 to the 9th? Come on. Come on. All right. Is this something that would work? Yeah, okay. So again, if we iterate through these in this order, then this is automatically satisfied. So we just get rid of this condition. So now we only care about this. And once again, we're doing a very similar thing to the previous problem. We can build a segment tree on the values of A, and then query on the range from 1 to bi minus 1 the maximum value of dpj. How many years? Let's see. This took me 2 years, although other people have taken longer. It's sort of like random how long it takes and a function of the effort you put in and some other constant factors I don't know about. So generally it takes multiple years, often a long time. All right, so the plan here would be we go from 1 to bi minus 1, and yeah, we build a segment tree on these values. So the annoying part is that these values have the 10 to the 9th, and I don't like that. I don't know why they would do that. But what we can do is we can sort of compress coordinates, because we don't care about the values themselves of these. We really care about relations. We care about what's greater than what. So compressing these coordinates, for example, say we had something like this, like 175, 2, 3, 2, 7, 6, 5, 1, 3, 7, 9, 3, I don't know, 2 billion, right? We know this is less than this, and this is less than this. And actually, wait, hang on. Let me make this a bit better. So we have 2 equal values now, and this is equal to this, and this is less than this. Then we can compress these to values between 0 and n minus 1, where we just make the smallest value 0, and then we make the next smallest value 1, and then we make the next smallest value 2, etc. And so this array will be compressed to 0, 1, 1, and 2. Because this would become 0, this would become 1, this would become 1, and this massive value would become 2. Because again, all we care about is what's greater than what and what's equal to what. We don't care about the values themselves. So we can compress them to this tiny range, and we have to compress AI and BI simultaneously, which is sort of annoying. So now we So like we have O of like we have 2n values in total of AI and BI possibly. So now we have the values between 0 and 2n minus 1. So that's nice. We can build a segment tree on these. Do you have to study segment tree before watching the stream? No. At the beginning, I did go over the brief basics of this, so it may help to just rewind and start that. It's also not necessary to like actually be following along with the stream. It's sort of just like a video you can also watch simultaneously. So anyway, we compress the coordinates like this. Then we build these segment trees over the values of A, and then we query the maximum. And then when we're finished with an element, we stick its DP value at its value of AJ so that we can query in the future. So actually, this is very similar. I need maximum instead of sum. And we're going to do some stuff here. So read into the values. These are all on one line. Okay. C into AI, then BI, and then HI. Set these to this. So then we want to compress these. And the easiest way to do that is just to like make a map of these. So we make a map, and then we're going to map the initial value to its compressed value, and then run all AI and BI through this map. So first, we want to create all these keys in the map so that we have a list of all the unique keys we have. In fact, I don't actually need this, which is sort of voodoo magic, but I'm going to leave it in so it's easier to understand. And then iterating in order of, in increasing order, because the map stores them that way. What we're going to do is we're going to simply assign it the lowest value that hasn't been assigned yet. So we start with 0, then we assign the next one 1, and then we assign the next one 2, and etc. And then we're going to compress these values and actually do that. This is a slow way to do compression because using a map is slow, but it's fine. It's not that big a deal because we are fast enough. And then we initialize the segment tree to be all zeros, and that's fine. We want it to be zeros anyway because we could also possibly just not have this at all. How does this work actually? If we can't extend anything at all, then everything will be 0 anyway, so that's fine. Yeah, so we have a segment tree. We don't need 12 of them. st.init 2 times n because we need that, and then c. Now, they're not sorted by BI, are they? Okay. So we're going to create pairs now and then sort them by descending order of their height. PI equals make pair. There are better ways to do this, but I don't care. AI, BI, and then their height. And we're going to sort it using a custom comparator. And this basically just tells it to sort by the values of B. So return a dot first dot second, which is again the value of B. should be greater than b dot first dot second. Which spells out BFS, which is cool. So we're sorting by B in descending order. Because this is less than. I'm not going to go that into custom comparatives because that's a very different topic. But this basically just tells it to sort by BI. And yeah, we're streaming. Good. And then now, store the answer. So how do we do this query? We want to so it should be pi dot second, the value of h. And then we're going to query on the segment tree the range. This should be 0, because I'm 0 indexing, to bi minus 1. If so, pi dot first dot second, which is again bi, is greater than 0. V plus equals the query. We know this query will always be at least 0, so that's fine. Of 0 and pi dot first dot second minus 1. Once again, just the query we do. Then dpj is equal to v. And we take the answer as the maximum of that. And then what we do is we're going to insert it into the segment tree at the position AJ. But first, we want to make sure, because this segment tree does addition, we want to make sure that we don't overwrite some other value. So first, let's get the current value at AJ. So it's pi dot first, or rather like AI. We're going to insert it at AI. Then if dpi is greater than at, meaning that putting this here would include would increase the answer, we're going to add that difference to set it to dpi. It may be easier to have set queries, but you can sort of do most things with addition anyway. So that's what that does. And then the answer is just the answer. All right, let's test it. Explicitly using DP to make this easier on the eyes also. We get 6. We get 4. Works on samples, so automatically it has to be correct, obviously. Yeah. Don't use that mentality. Test your code. This is a stream and there's no penalty for penalties, so it's fine if we get this wrong, but yeah. Maybe we do get it wrong. Oh, we actually do. Okay, wrong answer on test 4. All right, what's with that? So now we get to debug segment trees. That's fun. 10 to the 9th values are longs. That shouldn't be an issue. We have max t. All right, okay. So n is up to that. All right, so let's figure this out. First, we could actually like print the compressed values and make sure they actually worked. Let's see what's causing this. So let's compress to 0, 1, 2, 3, 4, 5. Equal value should be equal. So 0, 0, 1, 2, 3, 4, 5, 6. Okay. Sure. Say the compression worked with relative confidence. reading the values in the right order. I would hope so. So I'm gonna get a segment tree of size 2 times n. And, okay, so I is 0, I is less than n. We make the pairs. Then we sort them in order of decreasing by b, I think. Yep. It does happen often, that's true. So we sort them by that. Then we say the current value is the current height, and we could possibly extend it. Could possibly extend it. Oh, I see, okay. The problem is when we have equal values of bi, then it's sort of vague what we can do, because we can put everything on top of everything else. That's actually kind of annoying. I'm not sure how to handle that. So we have equal values of bi. How does this work? You can basically put anything on anything. Wait, why is that a problem then? Because we can put all of them together, right? Or okay, we want the one with the largest. So if we put all the BIs on top of each other, I guess what we want is we want to make it as easy as possible to put a new one on. And what that means is that we want the lowest possible value of AJ to exist. Meaning that in our comparator, we need a bit more. We also want to sort by A so that we want the lowest possible AJ to be last in the array. So if we have equal values of B, what we're going to do is instead sort by the values of A, and we're going to also sort descending. So A dot F dot F is greater than B dot F dot F. I think that should work. It's untested, but that's fine. You know, like Turris said, we can use the judge system to test our code. What? Segmentation fault. Wait, what? What was that? What? What crashed that? What was that? Did I lose the 4 or something? Okay, I don't know what that was. I guess we'll test it. Yeah. Why not? Take the advice of the greats. Test 30. Alright, cool. Guess that works. Is this one also tight on the time limit? It's like kind of weird. It's 300 milliseconds. Maybe I'll just make this 2 seconds to be nice no matter what. I don't know why they have 1 second time limits anyway. Don't think it's that big a deal to have it changed. Make this one 2 seconds too, because it's kind of annoying. Slightly cheating here, but that's fine. Oh yeah, that's true actually. You could also compress everything with the same value of B into a single disk. And then again, you still want the smallest value of AJ. So you could take the minimum of the AJs and then also sum their heights together. Yeah, that's another possibility. That's kind of interesting actually. Because then you can just run the DP and not worry about things. But even so, doing the sorting this way also works. So I've solved this, but I don't remember it actually, so it's kind of fair for me to resolve it. I know this one's convex hull, so let's just figure that one out. Let's see. So all this is now irrelevant. Delete everything. Okay. Alright, so I will now do this. And then the current problem is E. By the way, has this contest started yet? Not sure what's happened. The code rams I was talking about. (2 p.m. EST). Oh, it is starting later. Yeah, I was kind of confused on where that came from, but okay, that's kind of interesting. I guess there was a timing mix-up, so maybe it just starts later. I guess that's a thing. All right. That is an unfortunate mishap, but it does mean the stream can go on, so let's do that. I think it was just that the times were confusing in the first place, or I don't know, because 16 o'clock UTC would be like 30 minutes ago, so I don't know. Okay, we have Kalila and Dimna in the logging industry. So there are two jackals living in a huge jungle, right? The manager wants them to go to a jungle and cut end trees with certain heights. They bought a chainsaw from a shop. Each time they use the chainsaw on the tree number I, they can decrease the height of this tree by 1 unit. Each time they use the chainsaw, they need to recharge it. Cost of charging depends on the IDs of the trees which has been cut completely. If the maximum ID of a tree which has been cut completely is I, then the cost of charging the chainsaw will be BI. If no tree is cut completely, they cannot charge the chainsaw. The chainsaw is charged in the beginning. Alright, okay. I remember this having a weird statement. So the cost is the minimum value of B over the trees that you've already cut down. So if we sort by B, which they've already done conveniently for us, then that makes it nice because it means we can assume that the cost of the chainsaw is the latest tree. That is, it's the highest index we've done so far. And also because BN is 0, it means that when we cut down the last tree, we can instantly recharge everything else. So when we cut down the last tree, we're done. Because, yeah, that's how it works. So we're looking for the shortest time to get to tree I. Okay, so here are some observations. First, so let me explain this statement a bit better. We have some trees. We have some, let's just say we have some array values. Trees is sort of confusing. So we have something like this. We have some array values. And we have some other array values. Call this A, and call that B. And we have 5, 4, 3, 2, and 0. Then what we can do is we can so we start with like charge or whatever. And then in one move we can like decrease an array value by 1. And then when the array value is 0, it means we've cut down that tree. It means we're like done with that. And then when we use the operation, we lose a charge, meaning that like meaning that we have to spend some time to recharge it before we can do another move. And the time it takes to recharge it is the minimum value on B of every tree that you've cut down. So if I've cut down this one, and this one, then the time it would take to recharge would be the minimum one of the ones I've cut down, which is 2. It's not 0 because we haven't cut down 0 yet. So every time you do that, you have to recharge one. And yeah, that's the idea. It's also guaranteed that BI are descending and AI are ascending, but because we're using dynamic convex hull, which is the name for the thing we're doing, this isn't actually that important. It doesn't matter that this, apart from the fact that we can use the last value of BI to represent our cost for recharging. Other than that, it doesn't matter the way the values are sorted. So yeah, that's the basic idea. So you want to cut down all the trees, and the link, you can find the mashup in this description, and then it's problem, oh, I didn't pin it. It's problem E, my bad. Yeah. So first, of note, when we get this last one, we're done, because it has cost 0. That's a guaranteed part of the statement. So when we get it, we can cut down every other tree and not have to recharge at all because it's 0. So we're done. So we want to figure out the minimum number of time, not to do everything, but just to cut down the last tree. And the second part is that when we cut down some tree, we can ignore everything before it. Because again, if some tree is uncut, we can get it later when we finish it off with 0. And also we have to do this anyway, so we might as well do it as early as we can. And when we cut down some tree, that means we don't care about the ones before it, because this one is guaranteed to have a smaller value of B. So the only tree we care about is the previous one that we cut down. That being said, now we can define some state based on the only tree we care about. So now let dp of I, once again, be the minimum time to cut I down. So dp of 0 is 0, because we start with it charged, so we can immediately cut this down. And also a0 is 1, meaning that no matter what, we can always cut down the first tree no matter what happens. So then say we're solving here. Well, we're going to use some value of B to charge the chainsaw to cut this tree down. Which one are we going to use? Well, it depends. We can pick any previous tree and say that A, we're going to cut down this tree, and then B, we're going to use this charger for the chainsaw to now cut down this tree. Now, what's the cost of this? Well, we're picking some J, and then also we want the minimum of this. So we're picking some J, where J is less than I, so some value in the previous range. And then the cost is, first of all, dp of J, because that's the amount of time it takes to cut J down, plus, well, how long does it take to cut this one down? It's the value of the charger times this, because we need to charge it this many times, and this is how long it takes to charge. And also, when we cut down this tree, we know it's uncharged, so it's going to take exactly that. There's no indexing issues. So it's going to be B of J, this being the B value, times A of I, this being the I value. So now look at this. We have an intercept, we have a slope, we have an x value, and we can do convex hull. That's like it. This is a line, that's it. Now we just plug it into the convex hull and we're done. Like, some of these are really simple. Just find the recurrence and you're done. Yeah, that's it. So let's do that. So once again, we're going to copy in the convex hull. Close that. Copy in the convex hull. As always, you can find this on my templates if you want to try it. Then read in the input. Read in the values of A. Read in the values of B. and then I'm going to make a dynamic hull. Then we're going to what's value? 10 to the 5th. We're going to say dp0 is equal to 0, and insert the line of this, which has, and then again the line we're going to insert is dpj and bj. So the slope is going to be bj, and the line and the intercept is going to be dp of j. So for the first one, we're just going to insert that. So b0 and then 0. And we're going to find the recurrence. So dp of I is equal to the minimum line at AI. So the x value we use is AI. cht.eval AI. Again, a problem that we get is that the convex hull trick does maximum, we want minimum. But again, we can negativize everything and then take the negative line that we get. So for example, I'll take this and then this. So we negativize the inputs. So we can do negative b0 and then negative 0. And then we negativize the line that we get. And that gives us the minimum. Right. Now, doing that, we finish off by just saying cht.insert line. Actually, this should be, yeah. So negative bi and then dp, negative dp of I. And the answer is just that. I think this is like the baseline for the convex hull trick problems. It's the simplest one you could ask for. Because it's like, it's just the basic line form and that's it. And you put some slopes in. Seems like it works. Indeed it does. All right, now we get to more fun stuff. So, yeah, problem G is the one I'm scared of, so we'll get to that soon and then have some fun with it. But for now, I can do this. And yeah, and then pin that one. I'm just gonna continue chugging along and see if we can do all of this. I don't know how long this is gonna take. But anyway, that's convex hull. So we can do another segment tree one now. I picked this one to be a segment tree one. So you have a gift of multicolored pencils for his birth, right? So everything is the same color and only saturation differs. So the pack is n integers where the saturation of the color of each pencil is that. He wants to put all of the mess in the pack in order. He has an infinite number of empty boxes to do that. He would like to fill some boxes in such a way that each pencil belongs to exactly one box. Each box has exactly at least k pencils in it. Each non-empty box. So if you put a pencil in a box, you want to have at least k pencils in it. And if two pencils are in the same box, their absolute difference is less than some value of d. And the different way to represent that is there exists a bound, like there exists some value x where like every value is between x and x plus d. And if that's true, then it automatically means that every absolute difference is smaller than or less than or equal to d, because like this is the maximum, this is the minimum. And if this is not true, then you would have some difference that's greater than d. So the absolute difference of all pairs being less than or equal to d is equivalent to all values being on some range x and x plus d. That's one way to think about it. And you want to figure out if this is possible. Cool. Let's do some stuff. So, let's see. First, we can sort the pencils. Let's see. So we sort some pencil. So right, we have some pencils like this. So we have n equals 6, k equals 3, d equals 10. We have the values 7, 2, 7, 7, 4, 2. And, right, so first we can sort them. And then that sort of makes the absolute value condition nice because now actually we sort of don't even need the interval thing. Because we know that, like, say we take some range of this array. Then we know the maximum element's going to be here. The minimum element's going to be here. And every value is going to be between this minimum and this maximum. So the difference between the minimum and the maximum is equal to the largest difference between any pairs on this subarray. And the minimum is the lowest element, the maximum is the largest element. So now we're like breaking this into subarrays that make it work. Now, the other thing that's sort of annoying to prove is that subarrays are always optimal, right? Now let's say we didn't use subarrays, for example. Like, this is sort of an intuitive proof. It's not perfect because there are more cases, but let's say we didn't use subarrays. So we have two partitions, one that's like this and the other that's like this. That they're sort of disjoint and they are split apart by other partitions. Now I claim that we can always swap these two for a better answer. Because A, it doesn't change the sizes of the sets. So if this worked before, it would still work because the sizes would not change. And B, it's going to make the differences smaller. Because we bring this element closer to the rest of the orange ones, and we bring this element closer to the rest of the blue ones. Specifically, this becomes a 4, this becomes a 2, and so it's going to be better. So if we don't have ranges, we can swap them until we do have ranges, and the answer will still work. So therefore, there exists an optimal answer where we use ranges. And if there's no optimal answer where we use ranges, then the argument is that if there was some optimal answer that didn't use ranges, then we can transform it into an answer that does use ranges. Meaning if there's no answer that's optimal, or if there's no answer that does use ranges, then there's no transformation we could have done, so there can't be any answer at all. That's the argument for proving something like that, where you have a transformation and you can prove that the optimal answer has some certain property. It's like a proof by contradiction. Like, suppose there is some other answer, then you could transform it into an answer with ranges only. And then because there's no answer with ranges, you can't have some other answer. So that's the idea. So now we're taking subarrays. So this is where we get to the DP part. Let DP of I answer the question, is it possible for the range, for the prefix of I elements? So for example, DP of 4 would ask, is it or DP of 3 would ask, is it possible for 0 to 3? And in fact, I should make it 0 and be consistent with my own indexing, which I never am for some reason. So is it possible for 0 to 3? Now, that is the question. What is the answer? So the idea is there are two possible transitions. We can either have I be in the first box, or I in some box or like I is not in the first box. Okay, so the first transition simply asks, A, can we put I in the first box? And the first box, if we iterate this way, it means that the first box must contain all of the elements 0 to I. So we ask, is this box valid? That is, are there enough elements? Are there at least k elements in the prefix 0 to I? And also, is the difference between the largest and the smallest element, is it valid? Is it within D? And if so, then this is possible, and if not, then we don't know. Then this transition isn't possible. And if this transition isn't possible, then possibly we extend some previous box. So let's redraw this array, I guess. 2, 2, 4, 7, 7, 7. Now we're solving here. We want to ask if this is possible. So if this is not in the first box, then there's some other box that starts before it. For example, say it's here. Notice that, like, we don't care about this. We don't care about the other boxes as long as they're valid, really. So we're basically saying we're going to create a new box here. We're going to pick some other place to start a new box. We want this box to be valid. And we need the rest of it to also be valid. But we don't care about what the rest of it is. We only care that it's valid so that we could create this new box on top of it and extend this validity to this whole prefix. So really, it's like, this asks, is there a J where... Is there a J that makes this work? Let's say this is I, and we're looking for some J where J is greater than 0, because if this is here, then we're at the first transition, we're at the first box. So really, this sort of isn't necessary. We can like stick an extra element here. Actually, I don't know. It sort of depends on how you do it, but it might be easier to break up these transitions. So J must be greater than 0. The conditions are that AI minus AJ, because we know AI is greater than AJ because the array is sorted. Also, actually we can think of it like this. So 0 must be less than J, which must be less than I. So AI minus AJ is less than or equal to D. And in fact, this would be that what would it be? We have to have at least K elements. So there must be at least K elements between AI and AJ. Meaning that the number of elements we have between I and J is going to be I minus J plus 1. Plus 1 is because we're inclusive on both sides. So really it means that I minus J plus 1 is greater than or equal to K. So if we solve for this, if we solve for sort of J, then it means that J is less than or equal to, we move these around, I minus K plus 1. So we can combine these conditions. So first of all, we know that J must be less than I minus K plus 1. And actually, I don't know why we have this condition. This isn't necessary. It's not that important. So this is how it is. J must be less than or equal to, right? Less than or equal to I minus K plus 1. We also have this constraint. So what does this mean? Well, we can do something like, we can do, what we really want is we want another constraint of J. We're trying to get this into a range so we can use a segment tree on it. So instead of like making this a condition, let's just find the endpoint of the range where this is valid. And note that because the values are decreasing, there's a certain point x where everything to the right of x is valid and everything to the left of x is invalid, meaning that this is going to be the left endpoint of our range. So how do we find this? We can use something like 2 pointers, where we maintain one pointer to I, and then we move the other pointer to the first location where this is satisfied. Because that's our value of x. If we have this pointer represent the first location, then every value greater than or equal to that pointer will be valid. Everything before it will be invalid. And because these values are increasing, this pointer will only ever move right. So it's O of n, 2 pointers, same argument. I should make it 2 pointers mashup. Who knows? As top extremes go, not the worst idea. So yeah, so let this pointer be P. Let's just like call it that. Then J must be greater than or equal to P, because it can't be less than P, otherwise it'd be invalid. So now we have this range. J must be in between P and I minus K plus 1. And it also must be true that the rest of the stuff is valid. And this is asking if we're ending at this position, meaning that this would be dp of j minus 1. So we want to ask, does there exist a j in this range? So we can move these conditions here, where j is in this range that defines the valid things we can have. And dp of j minus 1 is true. With zero indexing, we get a dp negative 1, but that's just like a blank array, meaning that it's also true. Then if so, then dp of I is true, otherwise it's not. So really we're asking, is there a single value in this range where dpi is true? So say we built a segment tree now on these indices, where something is 1 if it's true and 0 if not. So for example this, then we're interested in querying this. Then we can take anything. We can take like the sum on this range. We just need to see, is there a non-zero element? So really like, in fact it doesn't even require segment tree. We can use a set or something like that. But segment tree is, well, that's the topic of the stream, so let's do that. This is it. We're asking, is there a value on a range that's greater than 0? Another way to think about that is you can do like bitwise or something, or we can just say we want the sum to be greater than 0. So we've reduced this to a sum segment tree. Imagine that. Yes, that's cool. And that's kind of just it. Yeah. So let's do that. So there are multiple things we have to do. First, the right bound is easy to compute. The left bound requires 2 pointers, which is not terrible. And we need the segment tree, and we need to do some DP stuff. So we can in fact 5 times 10 to the 5th. Why would they do that? I hate edgy rounds for this reason, because they like I have a beef with edgy rounds, mostly because I suck at them. But other than that, like, you know, I don't know. I mean, this is just an annoyingly large constraint. There's like not much reason to do that. Oh, we can do the maximum too. Like there are infinite amount of ways we can ask, is there a 0 on this range, or is there a 1 on this range? In fact, max kind of makes more sense, so let's just do that since I already have it. So let's see. We're going to read in the values. Then 4. Okay, now set b0 size of b is t dot init and b sort a. Now maintain the pointer, iterate through, and the answer will be dp of n minus 1. So I equals 0, I is less than n, I plus plus. We got some stuff going on. Right. So first, we maintain point. Right, we maintain point. So first, while our current pointer is too far away, okay, this is another mess. So let's draw a new array. It's 2, 2, 4, 7, 7, 7. Right. Whoa, what the hell was that? Don't do this, mouse. Come on. Sometimes my mouse just like jumps around, and sometimes it actually closes things, which is a really big problem, especially in Zoom school and stuff like that. So that's not fun. But yeah, that's a thing. Hopefully that's not happening now. That would be sad. I don't want to close Paint. Right. So we're here, for example, and while our current point is too far away, that is, while the distance is too large, move it over so that the pointer will be the first point that's valid. So we simply do that while. Also note that because of the way this is constrained, because d is at least 0, like no matter what, the pointer won't exceed n, or it won't exceed I. So while point is less than I, no, I don't even need that. I just said we don't need that, and I did it anyway. So while ai minus a point is greater than d plus plus point. That's the first step. Now we know we're on the range of point to I minus k plus 1. L right bound is equal to I minus k plus 1. So if this range is valid at all, if point is less than or equal to right bound, otherwise we don't have an interval. We have a degenerate interval that doesn't exist. So dpi is equal to 0. Then if this is true, we can try this. And also note that actually the way I'm setting this up sort of gets rid of this first case, so it's kind of nice. Because this first case is just simply j equals 0. Oh my god. You see that mouse movement? That's like it just went like that. That's what the mouse is doing. This is just j equals 0. And of course we have dp of negative 1 equal true, so that works. Right, so, okay, hang on. Yeah, I found that the best fix for this is just like slamming the mouse really hard. So let me try that for a second. Did you see that? This is working, right? Did you see that? It just opened 6 new files. Like, this is so stupid. But I guess that worked. Unless I just took it out and put it back in. Alright, so that was an experience. But anyway. So we're asking on this range, is the maximum value dpi equals st.query the maximum value on the range point to the right bound dot value. So that's it. And now we're going to update, and the value we use to update is dp of I minus 1. So allow prev is equal to 1 by default, and then if I is greater than, because dp of negative 1 is 1, so if I is greater than 0, then we overwrite it. Prev is equal to dp of I minus 1. then we update at I to be this value. Love from Mars. That's interesting. Never seen that before. What's it like being a Martian? Okay, we get yes. Can't click. We get no. Okay. I don't know if it works, but works on samples, so that means it's probably wrong. Let's try it anyway. Again, you should definitely test your code. Like, definitely test your code. Like, definitely test your code and don't be like this. Definitely test your code. Yeah, because you get stuff like that. All right. No, you didn't miss convex hull trick. I've sort of interleaved the problems. Like, some of them are segment trees. H... Actually, all of the last four are convex hull tricks. So, there's still a lot to come. Although the explanation was at the beginning, you can find it by rewinding, I guess. Definitely test your code, just saying. Okay, so we have value D. Read into N, K, and D for each value, C into AI. Now, initialize the segment tree to have all zeros, and then sort. Now, the pointer is 0. So while this is greater than D, move the pointer forward. Now, the right bound is that. We must have at least K elements. Wait, hang on. Is this I minus K plus 1 is the first position where we have at least K, right? If J is I minus K plus 1, then we have I minus K plus 1 plus 1. It's I plus K minus 1. Or K, yeah, okay. So I think that's right. That should be the right bound. And then set it to that. And we ask, is that possible? Interesting. Maybe there's some other mess with equal values. That was what the problem was on D. But I don't see how equal values would be an issue, because we can just like, it doesn't matter what's where, so we can assign an arbitrary ordering to them, I would guess. Is ponies a place? Or is that like a group? If it's a place, that's even more interesting. Like, what would that be like? Okay, each pencil belongs to exactly one box. Each non-G box has at least K pencils in it. We did the proof that it's always okay to do ranges. So something's up. 5 times 10 to the 5th. Which we do have. Should not be an issue. Do we have some things with sentinels? If RV is negative, then we don't care about it. If RV is negative, then we don't care about it. Okay, I guess we can try some edge cases. I don't know what's up with that. Hopefully the idea is not wrong. That would be annoying. Let's do like 6, 7, I don't know, 6, 7, a million, and then it should not be possible. And 6, 6. I mean, yeah, okay. So those are dumb cases. We are sorting. We are sorting indeed. It has to be at least K, but that's fine, because we're accounting for more than K. We are, right? Do we have some issues with like the beginning? Like say it's all one group. 3, 3, 10. Oh, we just did that actually. So it's like 6, 7, 6, 3, 1, no. 13, that should not be possible. And if we do something like 3, 3, 10, 6, 3, 13, that should be possible. And all right, so what's up? That is the question. Guess we can go over code again. So we're reading the values of A. We go up to N. Don't use K anywhere. Sort up to N. Use the values of B. And B is just the sentinel array to initialize the signature with, and it's okay to have it be 0. And we're asking for the maximum. I mean, there should be 0 or 1. Maybe it's one element. Is that a problem? Oh, that would be a problem. Would it? Yeah, it would. We want to do this first. Okay. That's the edge case that we have. If we have one element, we would say no, even though it is possible. So we want to do this first. If I can click for... Dude, my mouse. It like... It's unclicking. Oh my god. Okay, there we go. Retest on samples, though I think that fixes things. Yeah. Because we weren't considering taking J and having that be equal, or taking J and having J equal I. Because that would not be considered because we did the update afterwards. So we want to do that first. And thus, there we go. That should fix things. Pass test 10. There we go. Alright, 400 milliseconds. I guess in terms of time, that's fine. My mouse is not assertive, though. Like, it's not, it's weak. Can't even click that hard. Like, I could do this, but, you know, slam the mouse every time. Wouldn't be great for the mic, though. I don't think my viewers would like that, or myself. Actually, why am I getting rid of the segment tree? This next one is that too. Okay, let me just, I'll keep the segment tree. We don't need maximum. All right, so this one I haven't quite figured out yet, but it's also not easy. I wanted like one of the harder ones to be a segment tree one. So I'll leave that there. I wanted one of the harder ones to be segment tree. So that's a thing that we're doing. So here's how this works. Oh, by the way, are you guys interested in problem difficulties? I can say the difficulties of each of these. So these two are mine, so they're not coforces. This one's 1900, which means wait, this one's 1900, right? If I open on incognito, it'll let me. Oh wait, that's what I meant to do. Yeah, this is 1900. There's no like easy way to do this sort of demonstration. All the problems have to be not easy. So this one's 1900. This one's 2000. This one is 2100. This one I believe is 2100 as well. It's just cause these techniques are so rare. Like these actually come up quite often on educational rounds. And even some of the previous rounds, the harder problems have things that are like this. So they're not going to show up early, but they may show up later. So it may actually be worthwhile if you're getting good at DP and stuff like that to try reading the later problems. It's possible that it could work out. Possible, not guaranteed. Possibly not even likely, but possible. Okay. Vasya commutes by train every day. There are N train stations in the city, and at the I station, it's possible to buy only tickets to stations from I+1 to AI inclusive. No tickets are sold at the last station. Let PIJ be the minimum number of tickets one needs to buy to get from station I to station J, as Vasya is fond of different useless statistics. Nice. He asks you to compute the sum over all pairs. I am fond of different useless statistics too. Let's do this problem. So basically you have a bunch of trains like so, and each one can jump from itself to a certain range in front of it. Like for example, this one can go here, this one could potentially go here, and this one might go to all of them, who knows. But yeah. And then like maybe this one can go forward. And then using these jumps, we're going to fix some I and some J. And we're going to find PIJ, which is the minimum number of jumps required to get from I to J. So if there's a direct jump, for example, this could be 1. If there's not a direct jump, then we may need to take 2 separate jumps, and this could be 2. Because everywhere can jump forward at least once, it's always possible to get everywhere, so this value is determined uniquely. And it's going to be the minimum. And we want the sum of PIJ over all pairs. Okay, this is the problem I was talking about. I tried this for like a while, but it was also at 2 a.m., so maybe it's going to be better now that it's 12 p.m. instead. So we'll see how that goes. So n is 100,000, of course, like, you know, they're not nice with the constraints. I mean, they're not easy constraints. So let's find out what we're going to do. We're going to find the sum of these values. So the general idea with problems like this, where you want to count like the sum of a bunch of things, is to fix something. For example, say we fix the ending point. Now the question is, does that make it easier for us? And the answer is, I don't know. So let's see. If we fix some ending point, then we want to somehow move from this ending point to this one. We want to use the answers for this to make it easier to compute the answers for this. And so the question is, how does this work? And is it easier to do ending point at all? I would guess that the answer would be no. It might be easier to do starting point. So we iterate backwards, sort of, and then we use the answer for this starting point to figure out the answer for this one. So how would we do that? By the way, my audio is working, right? I would hope it is. Yeah. So how do we do that? Seems like it's making noise. Okay, so we're interested in something. I don't know what that something is yet. So say we have these values, like for example, like we know this would be 0, this would be like 1, and this would be 2 or something. Then this sort of like flattens this out. Or we say like, say this can jump to these two. Then this becomes 0. This becomes 0. This becomes 1. This will become 1. And then everything else is unchanged. Kind of. So the idea is, what gets changed? Well, yeah, it would be one more, but we want the sum, so it's sort of complicated how that would work. It's like we're interested in the ones that can reach I, but that's not necessarily an interval because each right point can be different. But if we fix the starting point, then we know we're working with an interval at the very least. So that might be better to pursue. Although I don't know. This one's annoying. So how does this change the previous values? Well, almost everything goes up by 1, I guess. Almost everything. What doesn't go up by 1? Yeah, the jump. Like, I mean, you can jump anywhere you want. The point is, this can jump from anywhere on some interval of values. But yeah, it goes up to n. Yeah, this does seem promising. Oh, hi, Steven, what's up? Nice to see you again after a while. Yeah, no, like, difficulties. Like, this is not easy. The first problem is 1900. This is not easy. And, like, the last problem, if you want to know what difficulty this is a 2900. In fact, it's really not easy. Like, if I could, here, do you want me to just show the difficulties right now? I could if you want. Okay, so I mean, I think there's some sort of like weird way we can update. No, this is only a 2900 because it wasn't well known. This is well known now. Like when I got this in a duel before and it took like 40 minutes or so. So I can resolve it. I only picked it because it's a sort of like nice culmination of everything. But like if you read it, you'll see what I mean. Here, I'll show the difficulties right now. I think if I go to manager mode, this will let me do that. Alright, actually, I'm not sure. It might not. Let me see if I can. If not, then that's kind of annoying. Maybe it doesn't. Okay, I can just say them though. This is 2300, this is 2400, then this is 27, this is 28, and this is 2900. So the last ones are even harder. But again, some of these like have much higher rating than they should, solely because the convex hull trick, I guess, wasn't as well known back then. But now it definitely would be easier now. I have 3 tabs of the same problem. Right, so does this sort of get like a convoluted chain of updates that we have? This could be longer than the previous range, in which case it updates things weirdly. This is sort of an annoying thing that I've been thinking about. I'm like not that big a fan of it, but it's something that's possible. Okay, say we have dp of I be the minimum or the sum of pij or I being less than j. So this is like the basic thing we're expecting. Then when we're interested in this value, this can reach some interval of values. let's say this. And everything else will kind of like, everything else will come from one of these values on this interval. And specifically one of them, I guess. It's sort of like whichever one on this interval has the largest reach, that's the one we're interested in. And so the reason I bring that up is because it's sort of like we don't care about what this is once we figure everything else out. Say like we have some element here that has the largest reach, so that every element after this is going to depend solely on this one plus an extra one because we have to jump from this one. So we have +1 for everything that depends on this. But what that means is that everything only depends on this, and then it's all that +1. So it's sort of like we just inherit this dp value here, plus like 1 for each one. So this whole blue interval, everything after the interval that we can reach from our current point, only depends on something else. So it's like we have this dp, except we have to specifically exclude, if I get rid of these messy drawings, we have to explicitly exclude the things that are already predetermined by this. So we specifically exclude this, because this is sort of already in the equation. So we exclude that part, and then we add 1 to all of these, and then we sort of inherit that. That was the idea I had. I'm guessing, I don't know if there's a smoother way, but I mean, this works, so why not? Means we also need the index of the maximum, and that's something that is kind of annoying to do. Let's see. So I can do something like this, and I think this would work. And I can sort of rewrite this to store indices too. Ind. Oh yeah, if you don't know Steven, twitch.tv/StevenK+, I think that's it, right? Yeah, go follow. You can see the profile picture is the same. Okay, does that link work? I hate that smile. Okay, that's an annoying emoji, but yeah. Anyway, this is gonna be buried in the middle, but you know, for what it's worth. dpi is a function of I, ai, and just... Oh, I see. Like it's like relating the values of dp to each other. Maybe that's possible. Yeah. That's true. Okay, maybe I should follow my own advice and like explicitly find the formula. Yeah, that's a good idea. I don't know why I'm not doing that. So, so dpi is some value okay. So transition would be that we want to like inherit it from some value, kind of. Is that how that would work? How much did I practice? It was like 2 years or something. It was a lot though. I did spend a lot of time at certain points, like many hours just grinding problems. It's going to take effort for sure. Okay, let's try to be smart. Maybe, possibly. That's the plan. Take some colors and just draw some things around. That's usually what I do anyway. So we're interested in the one that lasts the longest. Is there some other way to formulate that? Oh, I see. Right. I guess we don't need the index itself. How'd that work? Like currently we want the one with the furthest endpoint. And then our DP would sort of inherit that value. Perhaps there's a better way to think about it. I mean, writing a signature on indices would work. And it can't hurt to practice that, but maybe there is a nicer way. And that nicer way would be nice to find, because I don't want to write a signature on indices. Like, we want to find this magic blue ball, which I've turned into a different shade of blue somehow. In fact, I forgot what this thing was. I'm losing track of my own drawings. I guess it's kind of like this value would be minimized. We would want the minimum previous value of DP, but where we also have to exclude like the current interval. I guess that would be it. That we want the minimum previous value of DP. That's equivalent to finding the largest endpoint, because having the largest endpoint would give you the minimum possible value, I guess. And does that still work if we factor in the point that we have to subtract out this stuff? Does that still work? I guess it would. It's the way to do it that minimizes the sum. And if something can't even reach beyond this interval, then there's no way it's going to get anywhere. So we can assume that the best DP value will go beyond this interval. And therefore, like the interval we would subtract out would have all ones. So like this whole range would be ones. And then I guess it's good to do that. Okay, let me try re-explaining this. Less messy this time. So we're interested in finding the DP value for a current point, where DPi is the classic sum of Pij. So let's say this can reach this interval. So what we're basically interested in is we're going to pick some value, and then we're going to say that the optimal path is going to jump from here to here. Well, first of all, the optimal path to all of these will simply take this. But for all the things outside this interval, we have to take something on this interval. So let's fix the thing we're going to take on this interval. And let's say we're going to take this one, for example. Then what we get is the remaining costs that we get. So for example, say this can reach outside the interval. Then the dp will have all of these distances be like 1, for example. And then everything else will be like 2 or 3 or something greater. But the point is that in this, relative to this position, all of these are going to be 1. And relative to this position, everything after it is also going to be 1. So we can sort of subtract out the remainder of the interval that's already covered by this one. Is that even necessary? I don't know. It's either way it works, I would suppose. Actually, we can assume that all of these are going to be 1s, I think. Because if this can't even reach outside of this interval, then like why would we pick that one? That's useless. So we want to pick the farthest one, and it's guaranteed that like the last one will reach outside the interval. So something will reach outside of the interval. And therefore, instead of subtracting this out, we can just add the rest of the parts that aren't included. Maybe that's even easier. So we're at I. We're going to pick some j. And then what we're going to get is dp of j plus let's see, how would this work? So everything here is 1 no matter what. And then everything else outside will sort of be added by 1. Because it's necessary to do that. We can't reach them in 1, we have to reach them in greater than 1. And that means we have to take this jump, meaning that everything outside this range will have an extra +1 from taking this jump to that, and then taking this one. So say this is AI. Then this is going to be the size of the green range, everything gets 1. So it's n minus 1. Cough. Yep. n minus 1 minus, like the size of this green range is going to be n minus 1 minus AI. And that works. And it's inclusive of this and exclusive of this, so that is correct. And then plus the size of this range, which is going to be inclusive of I, no, exclusive of I and exclusive of j. So it's going to be j minus I minus 1. So reordering some things around. Wait, so dpi is the minimum where I plus 1, where j is between I plus 1 and AI, since we want it on this interval, of dpj plus n minus 1. Oh wait, it is inclusive of j. That's true, you're right, yeah. Because this has to be 1, and I guess we don't include that somewhere else. So that's true. Sort of stuff, yeah. Okay, so it's inclusive of j, so we don't subtract 1. It means we have exactly that. Separating stuff out, we get min I plus 1 being less than or equal to j, being less than or equal to ai, dp of j plus j plus n minus 1 minus ai minus I. So we can extract everything and be left with dp of j plus j. And in fact, this sort of fits more with the theme of the stream, that we're solving for things and separating. So that's kind of nice. Which topic am I teaching? This is dynamic programming optimizations using both segment trees and convex hull tricks and stuff like that. So I guess that's it. Now we need the minimum. Take the minimum, ignore the indices. And then we just, again, like before, we just stick into the segment tree these exact values. So yeah, let's do some stuff. Right, read in the values. So let's see, we want this to be huge. st.init and b. Can type for loops quickly, be proud of me. So now we're just going to do this. Let's see. So dp of n minus 1 is 0. dp of n minus 1 is 0. So sticking down to the segment tree, b n minus 1 plus b n minus 1 equals n minus 1. Let me initialize with that. Okay, so let's take this expression now. dpi is equal to n minus 1 minus ai minus I that should be a plus, not an equals. Plus st.query I plus 1 ai. That's it. st.update I prefer doing this just so I don't mess with doubles. So we update at position I for it to be dpj plus j, and then because we're doing addition, we have to subtract the sentinel value so that it's relative to 0. So dp of I plus I minus huge. And then ants is equal to ants plus dpi Yes, they do require convex hull trick. So yeah, have fun. See ya. Sure. Oh. Dot value, right? Always get this thing. Perhaps I should define the addition operator, but who cares? What's the value on n? 100,000. Should get 6. Don't get a value. n minus 1. Yep. We get 6. This one is the moment of truth. We get 17. Okay. Are we implementing this right? We implement the formula and just do it. Yep. Sounds good. Wish I can use brackets in code. That'd be cool. Got past test 3. Maybe that's meaningful. Got past test 8. Test 10. Interesting. Perhaps it works. There we go. Let's see. Where am I from? I'm from the US. That's... Yeah, I'm just in a state. What level is this? Now that's an interesting one. This is in fact a 2300. It's not easy. M-1 minus AI. So that's because M-1 minus AI is representing the green range. Everything outside the orange range will have to have 1 added to it, and that's just everything past the orange range, which goes up to AI. The problem's like weird like that. And then the other range is separate. So like this formula is like this corresponds to adding 1 to this. Let's see. This corresponds to having to add 1 to everything here, since this is sort of unaccounted for. Oh yeah, I'm just using 0 indexing, so it's like I'm like that. And then everything else is also relative to 0. I just use 0 indexing because I prefer that. Okay, so that leaves 4, and all of them are convex hull. And one of them also involves a segment tree. So that's cool. I can leave it at H. And then get that going. Cool, yeah. So, yeah. The fair nut got stacked in planar world. I guess stuck. You should solve this task to get out. You're given n rectangles with vertices. Yeah, n rectangles, where the bottom left corner is at 0, 0. For each rectangle, you're given a number AI. Choose some of them that the area of union minus the sum of AI of the chosen ones is maximum. It is guaranteed that there are no nested rectangles. Okay, that's also important. So let's look at this. What are these rectangles going to look like? So we have the XY or OXY axis, however Codeforces defines it, like so, and then we have some rectangles on it. Each rectangle also has a value AI associated with it. So let's take one of the inputs. Let's take the second input. So we have X value of 6, Y value of 2. Let's see, how far do we go out to? So 6. Oh, this is also a very, very common one in convex hull trick, by the way. That's why I chose this. So this is an X value of 6 and a Y value of 2. So we have this one, and its value is 4. This has an X value of 1 and a Y value of 6. And its value is 2. Sorry that that's not perfect. This has a X value of 2 and a Y value of 4. And this has X value of 5, Y value of 3. And a value of 8. Alright, yeah, so yeah. Good to have you here and have you remind me of my values. That was sort of overcomplicating that other one a bit. Although you could argue that going for the other formula was also an overcomplication. It may have been easier to write the segment tree and indices, but who knows. So anyway, that's what this looks like. And you want the area of the union to be maximum, minus the sum of the array values you take. Whoa, where did 40 viewers come from? What just happened? This like shot up by 10. Is this real? That just doubled. What the hell? Cool. Alright. Yeah, so basically we have these rectangles. We want to maximize the area of their union, meaning that no point is counted more than once. And we want to maximize the area of the union minus the array values we take. Okay, so first of all, the constraint we have is that there are no nested rectangles, and also that every rectangle is, has its bottom left corner here. Meaning that as x decreases, or as x increases, y will decrease. Because if we have some coordinates a, b, and c, d, where the x value is less than the other one, where a is before c, and then b is greater than or equal to d, then we get something like this. We get this rectangle. Oh wait, no, sorry. B is less than or equal to d. Then that means this rectangle is going to be strictly greater. And it can't be nested. Or not strictly greater, like it'll envelop it. And we can't have nested rectangles, so that's not possible. So it must be the case that if one rectangle's x value is less than the other, then its y value must be greater. Or greater than or equal to, depending. No, it must be strictly greater. So in fact, a must be less than c. You can't have two of the x values being the same. And b must be greater than d. So that's cool, because that means, like, using exchange arguments, we can show that as x increases, y has to decrease. Exchange arguments, or however you want to do it. Yeah, I'm still live. I'm planning to finish this. We're going to see how that goes. The second to last problem is going to be the hardest one for me. The others I already know how to do, so it's sort of cheating, but sort of not. Because the point is for it to be educational anyway. Right, so basically it's guaranteed that the rectangles are going to look like this. So the y values are going to be decreasing. So let's sort by x value, or let's sort by like the right x value. Then say we take some rectangle. Let's say we take this red rectangle. Then we're asking, what's the previous rectangle we took? Because we're interested in dp, of course. And it turns out that the previous rectangle we took is actually the only one that matters. And the reason that's true is because, say we took this one and we took this one. This one has a higher height than this one. And it's further. Meaning that whatever the red's going to touch of this rectangle, it's also going to be inside this one. And this holds for like all of the rectangles. So the only one we care about is the last one that we took. It's going to dominate all the other rectangles for all of these ones. Because this is higher, but it's farther to the left. And so we don't care if it's higher, because this is already lower anyway. So with that in mind, we can define a state that only depends on the last rectangle we took. So dpi is equal to answer for the rectangles 0 to I, assuming that we sort the rectangles by x coordinate. The answer for 0 to I and taking I. So the last rectangle you took is I. So then the transition is, you could have either you didn't take some rectangle at all. So you don't take a previous rectangle. Then the answer is just xi times yi. Like you get the full rectangle minus ai. Otherwise do. Then there's some j, and you want the maximum of such j's, where j is less than I, and the cost is what? What is the cost? Well, this rectangle is going to be at position xj, yj. How much more rectangle do you get? Well, the height of this rectangle is still going to be yi. This is xi, yi. The height of this rectangle is still going to be yi. And the the new rectangle you get is going to go from xi to the previous xj and then be stopped there because you already have this rectangle because you already took it. So the new rectangle you get is going to be the rectangle between xj and xi and the height being yi. So the area of this rectangle is going to be xi minus xj, noting that xi is guaranteed to be greater than xj, times yi, plus dp of j minus ai, because you also have to incur that cost. So let's mess with the formula as we always do. Separate the i's and the j's. That is the important trick that we're always going to do. So xi times yi minus xj times yi plus dp of j minus ai. Let's take out everything that doesn't depend on j. So we have xi times yi minus ai plus the maximum of negative xj times yi plus dp of j. Which last part? The part where we get this formula? Like the area of the rectangle is going to go from the previous x value to this one. So the area is the subtraction of these. Then the height is going to be this. So the area we get is the multiplication of the left and right. And then this is just dpj because that's the amount we already have from this. And then we subtract ai because that's part of the cost. That's what the problem says to do. And now we're just messing with the formula so we can isolate the I part and the j part. And by the way, like we can assume the diagram looks like this because of the fact that we have no nested rectangles, that it's going to like go diagonally down kind of. So this the new rectangle we get, this amount, is always going to be determined by this formula. So right, plugging stuff into convex hull. This is the slope. This is the intercept. And that's it. And this is the x. I dropped my pen because we're done. That's it. That's the formula we need. So we just stick these lines into the convex hull and we're done. Oh, actually, I can't drop my pen yet because I need to fix this. Yep, okay. Face reveal at 1 million subs. Yeah, we get stuff in the previous one too. Like, we're only interested in the new area we get. Now, face reveal is happening at 10,000. That's what's happening. We need to get to 10,000 and then I'll actually do it. So if we can get this number up quickly enough, we'll do it. That means you guys have to cooperate with me, you know. Okay. So we're gonna read this in. C into n, and then pair. And we have 1 million for some reason. It's kind of a lot. Yeah, 10k subs. That's what it is. I will follow through with that. Probably not precise. Probably not exactly at 10k subs, but like, you know, pretty close. My next topic. That depends, because I always do it. Like, I always hold a poll for them so people can vote on the topic they want, and so people pick this, so I'm doing this. So I'm probably going to keep most of these. I might add some other interesting thing, like maybe 2 pointers or something. That's a potential one. See how people are interested in that. And but yeah, it's gonna be one of like the 5 options that people can choose. So it depends. If you have new topics you want me to try also, feel free to let me know. I can include them in future polls. Although please not like FFT or something. I don't know FFT. Actually, I don't know convex hull trick either, but I mean, I don't know like the code for it, but I know how it works. But I don't even know how FFT works, or like any way to use it. So hold that one back. Save it for smarter people like Anandoza or Demoralizer or something. Or Steven, or like one of the other LGMs. Maybe they can start doing topic streams too. But for now, it's less relevant. We're going to finish up this problem. Dynamic hull CHT. Then we're going to do some DP stuff. How much has happened? Well, I've done the first 7. The basic explanation came when I was doing these two. So if you want to understand the basic prerequisites for this, go into the beginning of the stream. We'll do that for you. Right now, I just derived the formula for this 8th one, and so we're doing that. So if you want to see that derivation, also possibly rewind. Okay, let me implement this and then I'll get to more questions. So AI is less than or equal to xi times y. Okay, so for I equals 0, cn to pi, we just do that. Because it'll read x, then y, then a, so that works. P plus n, 10 to the 9th. Wait, this is gonna overflow? No, it cannot overflow. No, okay. Because the union is at most 10 to the 9th squared. Okay, so L ants equals 0. For L equals 0, I is an n, I plus plus. So we may not take a previous rectangle, and we say dpi is equal to pi.first.first, which is the x, times pi.first.second, which is the y, minus pi.second, which is the a. Otherwise do, and we need to have at least one line if we do. So let's say if I is greater than 0, dpi is equal to max dpi, and the transition is same thing, xi times yi minus ai plus cht.evaluate at the point yi, which is pi.first.second. Then we insert the value, the slope of negative xi, negative pi.first.first, and the intercept of dpi. So we have 9, we have 10, and hopefully we don't overflow and the convex hull is good and we go up to 10 to the 6th and whatnot and whatever and we're good. Yeah, I hope so. We're doing a very strong verification of this code. So as we wait for this to judge, let's just look over how we did this, right? So we make a drawing because understanding things is nice. And then we figured out that the fact that there are no nested rectangles is quite important. And what that means is that now we can define a recurrence because we can know that the last rectangle is the only important one. So we define this recurrence, and it's naive, and it takes O of n squared, and it's not a good recurrence. But the idea is we want to mess with it to try and force convex hull to work. And the way we do that is we isolate i's and j's and we look for this line form. And if it works, then it works, and if not, then it doesn't. But that's the idea. We're forcing a line form. And for a segment tree, we would force the i's and the j's to be entirely separate so that we can stick the j's in a segment tree. That's how this would work. And it's not necessarily obvious that there's going to be a line form. In fact, we had to force it a bit. We had to mess with the formula to make it so the i's and the j's were separate. But that's sort of why you have like many possible things you can try. You could play around with it a bit. You can say, why don't we try doing convex hull here, even if you don't know that it's going to work? And you can mess with the formula. You can see if it does work out. If it doesn't, that's fine. You can try something else. But if it does, then you get accepted. Perfect transition into almost TLEing. Yeah. I guess that's fine. I don't know. Should I make the time limit for this one higher too? I guess Python's like not nice. If anyone wants to use that, then it's not going to be that nice. So maybe I'll make this higher. I'll make it like 5 seconds or something. Just to be nice. Were we close on memory in any of these? Oh, we were. 149100. By the way, you guys should be able to see tests, right? That should also be a thing. Like you can see the actual values. So if you get wrong answer, you can look at that. Should I raise the memory limit here too? I don't know. Why not? Actually, wait, they use time limit scaling policies. So maybe it's not that important to raise the time limit. But you know, whatever. It doesn't hurt that much. Okay, so XOR tricks, that's a possibility. Sure, I'll have that as a thing. Alright, so we have 3 problems left. As I mentioned, all these are convex hulls. By the way, this difficulty is a 2400. And it just comes down to this. Make a formula. Make the recurrence. Find the line form. That's it. Do it. That's it. It's going to get more complex later, of course, but this is how it gets for now. Make the recurrence. Why can't I click? You see what's happening right now? Like, it's just undoing my click. It's so weird. Okay, so we have 3 problems left. Alright, I'm gonna go to the bathroom because I did drink a lot of tea, so that's probably a good idea. And I'll be back in a bit. And I'll draw a cute little convex hull so we can... There you go. There's your image. Mute my mic. Am I planning to go to MIT? That would be nice. I have applied. I don't know if it'll work, but I have applied. So that's possible. Yeah, I'll be right back. Alright, here we go. We are back. Audio's working, right? Yeah. And I also just realized, because this is a split stream, I should have also drawn a segment tree to make it fair. So I'll do that now if you're... to make you guys happy. Oh, that's kind of too late, so that's unfortunate. And put a segment here. But you know, whatever. Yeah. So now I can erase everything and then get my comments, or get my chat back up. Oh yeah, the people that stick around to the end of the stream are the true heroes, because this is where it gets boring and really hard and stuff like that. So let's see. Okay. Do I like code blocks? I had problems. I tried code blocks before, but I had problems because I used to use Replit and all of my templates were in like the web format. So none of it would load on code blocks, and it kept compiling really weirdly, and it just it didn't work. So I couldn't do that, although it did seem like it was nice. But when I used Notepad++, it was cooler. Like, if you guys want me to get more subs, I have plans for some cooler things. I'm gonna eventually make like a general just algorithm thing that should possibly blow up, and I don't know. I have some plans for videos that can get big. I don't know. We'll see. Oh, currently I'm using Notepad++, which it works. Using Notepad++ for the text editing, and then a thing called Sigwin, which is like Bash for Windows, to compile. So it's like basically text editor and terminal. That's how it works. Let's do this. Current problem is I. We have 3 left, and this one is escape through leaf. Now this one combines... Now this one's going to combine convex hull trick with trees, so I'm going to leave this in. Now here's how this works. You have a tree. You have a tree. Let's take an input. So for example, something like, and it's rooted at 1. So you have a tree, you have that, that, and that. Let's make the tree bigger. Do some more annotations on it. Okay. These trees have 2 values, AI and BI. Let's make AI red. Let's make AI green. So 5, -10, 5, and 7. And let's make BI blue. So -8, -80, -3, -10. And how does that come out to -300? What? Oh, -AT. Okay. That is a thing. And here's what you want. Am I using a drawing pad to draw in paint? Yes, I am. Wait, hang on. I'm interested in how this works now. Oh, the minimum cost, I see. Okay. So you're going to start at a node. Yes, I know. You want to see my analytics? I can show you just how much of my audience is from India. It's insane. Let me see. Audience. Yeah, you see, it's like absolutely dominant. That's just how it works. And then there are a lot of people who don't have countries, I guess, and they're unidentified, so I'm not sure where they're from, but definitely, completely dominant. So yeah, that's why I do my streams at like I calibrate everything to work for IST now because that's just sort of how it has to work. That's why I release videos at like 12:30 midnight because it's nice on the weekend and stuff like that. How to move from div 2C to D. I would say it's sort of the same as like at some point you weren't able to solve C's and now you can, right? Just do the same thing. Like any specific point isn't anything special. It's just the next level of problem that's harder. Maybe div 2Ds have like specific topics that may show up, but like so do div 2Cs. It's the same process you would use to practice. And what you can do, I can register for that. Cool. And what you can do is like take some contests and then take like a bunch of different contests and just look at their problem Ds, being careful about that wording, and then just see like what it requires. And yeah, and then you have like a lot of like different things that could possibly show up on D problems. Okay, I've gotten very, very sidetracked from this problem, but that's fine. Questions are the point of the streams, so cool. I haven't even explained the statement yet. So you have a tree, you have a values AI and BI. You start at some node. In one move, you can jump from a node to a child of it. Any child of it, like any child inside its subtree, where a subtree is just like any node below it. So I can jump from here to here, and I can jump from here to here, and I can't jump from leaves to anywhere else. So the cost of a jump is the value of, I think it's AI times BJ. Yeah. So if I jump from node I to node J, then the cost will be AI times the value of BJ. So for example, this would be negative 400 because it would be 5 times negative 80. And this jump will be 5 times negative 3, which is negative 15. And this jump will be 5 times negative 10, which is negative 50. You want to get from your starting node to a leaf. And a leaf is simply a node at the bottom of the tree, one that has no child. So like these two are leaves. And yeah. So you want to perform some sequence of jumps from some nodes to children nodes to get to any leaf. And the way to do it will be to I mean, like, yeah, that you can go to any child and you want to get to a leaf. And so you want to do it in a way that minimizes the total cost. Note that because cost can be negative, the minimum could also be negative. But you want to minimize the total cost. And this is rather similar to my initial problem, except like now it's on a tree. So this is like level 2. And in fact, I meant to include this in the statement, but I forgot because it was 2 a.m. and I was tired, so whatever. Time complexity and height of the tree. Are you thinking about perfect binary trees? Like a perfect binary tree is one that looks like for example, like this, where every node has 2 children. Like the tree I drew earlier, actually. It's the same tree. Where every node has 2 children, every node has 2 or 0 children, and all leaves are the same depth. That's a perfect binary tree. Or you could have something like that, which is like a binary tree, but it's not perfect. Or other things. I'm not sure. Like it depends on the input and the things you want. But for a general tree, it can look very different. Like it doesn't have to be binary. A node can have more than 2 children. Like for example, I can have this weird thing. and then just like have this stuff going on. So it kind of depends. Okay, let me try to do this. So you want to make the jumps, and you want to figure out the minimum cost to get from this node to a leaf. Except you want to do that for every node, not just this one. So like you want to do it for every node. Okay, so how do we do this? Well, this is a DP stream, and it's a convex hull stream, and it's a segment tree stream. But we don't need the segment tree part, because actually it might actually be easier to write a segment tree over convex hulls for this. But let's not do that, because I don't want to do that, because we'll do that later. And my Discord is in the description. Oh, there's also like a different competitive programming community Discord or something. Yeah, so let dp of I, how many times have I said these exact words in this stream now, be the minimum cost to go from I to a leaf. Any leaf, as the problem says. It's fine. The minimum cost to go from I to any leaf. Then, like say we're here. What we can do is, to compute this value, we can jump from this position, and then we can go down. And then we can jump from this position. I'm pretty sure the mic caught that. We can jump from this position to anywhere down. And if we jump from node I to node J, then what we get is the cost AI times BJ plus whatever time it takes to get from this to a leaf, which is dp of J. So we add these together, and then the total cost we get is AI times BJ plus dp of J. But this is special because it's on a tree now. So this is sort of complicated. Specifically, we want the minimum over all J, where J is a child of I. It's the minimum over all J where J is a child of I, of this cost, of AI times BJ plus dp of J. Yeah. So, look at this. Slope, intercept, x. We push on, we get this. But the problem is we're on a tree, so this is not easy, because this condition is not nice. It means we're interested in some subtree. We're interested in everything in its subtree and nothing else. So there are two ways we can go about this. One, we can use something called preorder traversal. And what that basically does is it's a magic way of numbering the tree so that every subtree forms a range. So what I mean is, like, say we number it like this. So 1, 2, 3, 4, 5, and 6. Now the subtree of this node will form the range 2 to 4. The subtree of this node will form the range 5 to 6. The subtree of this node will form the range 1 to 6. Every subtree will form a range, meaning that if we're interested in doing this sort of thing, we can build a segment tree over convex hulls. And that will let us query inside a specific range the maximum, or this value, the minimum of this value. A segment tree over convex hulls with a preorder traversal. This is one possible way to do it. This is not the way I'm going to do it. Segment tree over convex hulls will show up later, but I don't want to do it right now because I want to show variety. There's no point in solving the same two different problems in the same way. Let's do some variety. So that also means I'm not going to explain how preorder traversal works. There's probably tutorials for that, like, everywhere. Like, you can search it up on Codeforces or search it up on Google and then open Codeforces from there. Instead, we're going to do something else. Let's think of a naive solution. Let's do tree DP where we sort of build up like convex hull tricks iteratively. Note that we can insert, but we can't delete from a convex hull trick. We can insert however we want, but we can't delete. So let's say we're interested in computing DP of I. Now, we're going to first compute everything below it. Meaning that inside some node, let's say this is like node A, node B, and node C. Inside this, somehow we needed some sort of convex hull query structure, or we needed some sort of convex hull trick corresponding to this subtree so that we can find the answer for A. And we have a separate convex hull data structure for B, and we have a separate one for C. And somehow we want to combine all of these to form one for this node, I. And then once we combine them, we could simply query it and be done. How do we do this? Because if we do naive combination, this could manipulate at most O of n elements per turn, or per node, meaning that we would get O of n times n log n, or like O of n squared like log n, which obviously is not good. That's worse than just naively doing the DP, right? So let's not do that. Let's instead do better. We're going to say that we want somehow we want to speed up this merging, because the querying part is simple. We make at most one query per node. We just simply query the convex hull. The merging is the slow part. So the trick I propose is consider the sizes of the subtrees. The size of the subtree is going to be exactly equal to the number of lines in each structure. So say this is size 17, then there are going to be 17 lines in here, or at most 17. This is going to, say this is like 100, then there are going to be at most 100 lines. There could be fewer than 100 because some of them are removed, is the way convex hull trick works, but it doesn't matter. We're interested in upper bounds here. So we could have 17 here, we could have 100 here, and then say we have 5,000 here, right? Now imagine, instead of rebuilding the entire structure, we just sort of like take this child structure and we use it for this one. That way we don't touch any of these 5,000 lines. What happens is we keep this structure and we merge the rest of them into it. And so for every node we would do this for the largest child. And therefore the number of nodes in the largest child are not affected. The only ones that are affected are the ones in smaller ones. Meaning that the total amount of merges we use is simply 100 plus 17, which is 117, and not 5,117, which is so much better, right? Yeah, I mean, I know it's SAC. I'm just like, I'm leading into it. And so the idea is for every node, we're going to take the biggest child. And we're going to take its data structure and like steal it, and then not reinsert any of these lines. So this is going to save our complexity definitely by some. I mean, look at this. It cuts down our complexity by a factor of 50. That's huge. But how much better does it do? How much better does it do? Well, we want to think about this a different way. We want to think about a particular element or a particular line as it moves up the tree. Consider it moving into this child. Or consider it moving into this parent. So if this is the largest child, then it's not part of the complexity because this line doesn't move. It stays in its data structure, and this data structure continues upwards. So if this is the largest child, it doesn't matter what happens. Otherwise, say it's not the largest child. So there's some other child that's bigger. Let's draw a bigger node. Let's draw a bigger node, and then we'll say that this is bigger than this. So therefore, this does move into this new data structure because this one is copied from this one. Yeah, demoralizes here. Hi. So when this moves, it's going to add a log of n. It's going to add a log of n to the complexity. But the key point here is this is bigger. So say this is x, and this is y. We know that y is greater than or equal to x. And we know that now the size of this subtree is going to be x plus y plus 1. But y is greater than x. So x plus y plus 1 is greater than x plus 1. Or greater than or equal to x plus 1. And this is equal to 2x plus 1. So when we move, we go from this line moves from a container of size x to a container of size at least 2x plus 1. Meaning it doubles. And so whenever we move an element, the size of its container doubles. How often can something double? Well, this is the definition of the log of base 2 of n. You can drop the pen again, because now, because that's it. We just proved that every element moves at most log n times. So we have n elements. All of them move at most log n times if we do this strategy of stealing the data structure of the largest child. And we have an extra log n because each insertion takes log n. So we have n times log squared of n. So 3 seconds, 10 to the 5th, these bounds are fine. We can do this. Now, this is called, yeah, I mean, no, I'm not like deriving it on hand. I'm explaining how it works because it's not like I'm proving it for the audience, you know. So yeah, as Demoralizer says, this is called many different things. It can be called SAC or DSUN tree. I usually call it small to large because you merge small ones into the large ones and don't touch the large ones. But whatever you call it, its complexity is n times log n times log n times the complexity of moving an element. In this case, it's n log squared n. So that's it. We do this sort of tree DP, and as we move up the tree, we merge the convex hulls of the children to form the new convex hull of this parent, except we only do it except we only we start off with the structure of the biggest child, and then we move all the smaller children into that structure. That's the explanation of it. And then to answer for a node, we just simply query the structure and find the minimum of this expression. So for once, the convex hull part is not the hard part. The hard part is the rest of it. Why did I cross that out? I don't know. I think that's my mouse spazzing out. But the hard part is this. N log n and Lee Chow tree? How would that work? I don't know. I actually don't know really how Lee Chow tree works either. Maybe it works. Maybe like there's some fancy stuff you can do with optimizing the pre-order traversal, but I wouldn't know, so I don't know. And if I haven't said it enough, I don't know. Yeah. Let's see, let me look at the chat now, because I think I've missed some stuff. Should you solve A2OJ ladders? It's like a bunch of coforces problems, right? So I think that's, yeah, that's a good thing. My first name is Colin, but you can also call me Galen. I don't care. Because some of my teachers call me Galen because we have multiple Collins in my class. So I really don't mind which one. In fact, you can even be consistent. You can call me Colin one day and Galen another day. Doesn't really matter. Not Galen's son. No, erase that message. Erase that message. Just like delete. Yeah. But anyway, So yeah, small to large, stack, DSU and tree, whatever you want to call it. Point is, we're going to optimize this recurrence. So now let me show you how to implement this thing. I mean, it would have been in the video no matter what. It's in the chat, so like, doesn't matter. Also, I have an idea. Shoot. Yeah, this should be good clickbait. Boom. Then now we can do that, and then yeah, and then we're gonna read in the tree. So vector LL edges of size 1005 may also help to have children. Actually, it's not that necessary. Yeah. So then, actually, we don't need to store the biggest child either. So yeah, now we're going to read in the tree with a big grin on my face. Which you can't see yet, but you will be able to soon, perhaps. Edges U to push back V. I'll change the title when the VOD goes back up, but as long as you're still here, I'm allowed to do that. Yeah. Okay. Okay, so we're gonna define some DP. Then, so then what we're gonna do is we're gonna use pointers so we can do this stealing thing without having to reallocate everything. And the pointers make it kind of weird, but like it's yeah. Yeah, I'm gonna look, my criteria is clear for Facecam. It's very, very clear. I don't care how you do it. Actually, I do care how you do it. Don't bot me. But get this number to 10,000 and I'll do it. Don't bot me, though. That's going to get my channel banned, and that's going to be stupid. So don't bot me, but, you know. Get that number to 10,000 and it'll work. Yeah, you can use me for clickbait, too. Although, I think at this point, I have more to gain. I have more to gain from clickbaiting you than you do from me. Your videos get like twice my views. Okay, so let's see. So we're gonna find the biggest child. Jeez, I just flung my mouse across the table. That's cool. Size 1005. So first, size V equals 1. So then, let's just do children first. Wait, is this worth it? Yeah, it's worth it. Okay. So, for each possible edge, if it's not the parent, child v dot push back x. This is redundant, but it doesn't matter that much. So, you want to see the concurrent graph? I think it goes up a bit. Or it's steadily increasing. Now it's at 40. Now it's at 44. That's at 44. Let's see. Maybe it'll go up more. Look at this, guys. We have demoralizer. Come stay. Okay. I might stop. Probably not, but I might. So then we're gonna do the DFS and size, and then we add that to our current size. So if we have no children, then we're sad. And I don't have children. No, I'm kidding. Well, I'm not kidding about that, but I'm not sad about it. So if we have no children, then we're a leaf. So dp v is equal to 0, and we insert the line. Oh wait. So CHT v equals new CHT, and then CHT v dot insert line of the slope we want is the m we have is that, the slope we have is that, and the intercept we have is that, and we want to negativize it because we want the minimum. So we're going to insert the lines negative bj minus dpj, so it's negative bv and negative dpv. Will you be my Valentine? I don't know. I kind of want to know people. Kind of want to get to know people first before we get to that stage. Who knows? Maybe someday in the future. Should have a comma here too. Okay. Otherwise, we're not a leaf. So we're gonna store the biggest child, and this is the size of the biggest child, and this is like the child itself. So if size x is greater than the current biggest size, big size is equal to size x, and big child is equal to x. So obviously this will find at least one node, so it'll find the biggest child if there's a child at all. If not, then we'll get to this case. But otherwise we do. So first, what we want to do is we want to inherit the container of the big child. So CHT v equals CHT big C. That's just setting a pointer equal to another pointer. So this is O of 1. It does not actually move the container. These are pointers. That's why it's important to use pointers. Then for every child that's not the big child, for each line in how does this work? Line L. I don't know if this will compile, but I think it's possible. Line L star CHT X. CHT v insert, we're using arrows because it's pointers, L. Is that how that works? I think we can also use I don't know. L dot M L dot B. I've done this already, but it's like years ago, so pretty much solving on the spot. Or it's like a year ago or something. Because, you know, everyone like does this problem when they learn convex hull. It's just a while ago. I guess this works. There's also some iterator stuff, but I don't want to mess with that, so it's not. So then the query is dpv equals negative CHT, yeah, v arrow eval of AI, so AV, and then CHTV insert line for... I feel like I'm missing something. Because I remember this being more complicated, so I don't know. Am I missing something? Negative BV, negative DPV. What am I missing? Edges, child, CHC, DP size. I guess that's it. Oh no, I'm scared. Oh wait, dynamic hull. Oh, and I should use the pointer notation. These pointers are weird. No, I mean, it just, I like, this function was longer. I remember that. Okay, so it crashes, so that's cool. That's expected, though. Let's see where it gets before it dies. Gets to 2, 3, 2, 1, 0, negative 1. Oh, it gets to the leaf. Shall v dot size equal to 0. Some sort of point. Oh, I should return. Yeah. Okay. And these tests are really weak, so I don't know if that's gonna work, but I guess it's possible. I mean, we know that because there are at least 2 lines in this one, that it's going to have at least 2, like it's going in the right direction. Taking negative is right. I just don't know if it's going to be correct. But that's okay. I don't care about wrong answers. There's no penalty. We're streaming. So that's fine. Contest is over. Why does it keep telling me that? Oh, it took a while. It's passing. Nice. Did I ever have a girlfriend? Actually, no. The answer to that is no. And I'm sort of in a weird spot about that. Oh, I just forgot to update that. Let's see. No, I felt like this function was longer. Let me look at my original implementation to this. What college did I get into? I don't know yet, because I applied to everything late, which was not the smartest move, but yeah, that happened. Huh, it was like the exact same thing. Interesting. Actually, yeah, this is like literally the exact same code pretty much. Alright, sure. Yeah, I guess it did feel more complicated. But this was written a year ago and I don't remember it, so it's fine. Yeah, it's like November 2019. Interesting. Okay, cool. So, yeah. And this time I feel more secure about it, like there's less indexing stuff going on. Oh, wait, I did not. I submitted that as a manager, so I should resubmit that. It should be insta accepted. Yeah. Because if I submit as manager, then you guys won't be able to see it, so that's kind of unfortunate. Cool. Where do I want to go? I don't know. I'm gunning for some of the big places, like potentially somewhere like MIT. I haven't applied to many Ivies because I'm not that interested. But I don't know. I guess just somewhere that's highly regarded would be nice. Can't be assured that that's going to happen because the U.S. process is vicious, but maybe. Actually, it might not even be as vicious as it is in India. I know you guys have like a crazy exam, so I don't know how that works, but it seems not nice either. How do I do a 4-hour stream without dying? I eat lunch quietly, but also not quietly. This might come out to 5 hours, depending on how long this one takes. Throat's really dry now. What job do I want to get? Potentially, I don't know, probably some sort of developer. I'm like kind of into that. That kind of thing. Or engineer or whatever it's called. Lion tamer? I'm not so sure about that one. I mean, maybe. This is J, right? Alright, actually, I have a better idea. Okay. Stronger clickbait. So, did I get pinned? I did not pin that. So, Kostya is playing the computer game Cookie Clicker. The goal of this game is to gather cookies. You can get cookies using different buildings. That's in italics. You can just click a special field on the screen and get the cookies for the click, so you can buy a cookie factory, an alchemy lab, a time machine, and it all will bring lots and lots of cookies. Woohoo! At the beginning of the game, time 0, Kostya has 0 cookies and no buildings. Yeah, I'm gonna make the next topic stream easier. I don't know why people voted for this, because this was bound to be hard, but like 40%, and therefore like, what would that be? Like 500 people voted for this topic. So, I don't know. That's how it goes. At the beginning of the game, Kostya has 0 cookies and no buildings. He has n available buildings to choose from. The ith building is worth ci cookies, and when it's built, it brings vi cookies at the end of each second. Also, to make the game more interesting to play, Kostya decided to add a limit. At each moment of time, you can only use 1 building. So it's discrete, it's integers. Of course, you can change the active building each second at his discretion. It's important that Kostya is playing a version of the game where you can buy new buildings and change active building only at moments that are multiples of 1 second. Okay. Kostya can buy a new building and use it at the same time. If Kostya decides to use a building, I'm trying to pronounce it in a different way each time. If he starts to use a building at the time moment t, you can get profit from it only at the moment t plus 1. Kostya wants to earn at least s cookies as quickly as possible. Determine the number of seconds he needs to do that. Yeah, I guess, I mean, this will also be a long-standing resource for people even when they get better. Even if it's too hard now, it won't be later. Because again, a lot of this comes down to just manipulating like manipulating equations to figure out stuff. Okay, what if I do this? So if I like make it backwards. So if I like if I copy this here. Why is my mouse not working? So I copy this here and then get rid of that. And then I like put it backwards so that I can like make it there we go. Nobody's gonna understand this without context, but that's fine. Are you happy now? So right, so you have n and a desired number of cookies, and you each building has a value or a price and a amount of cookies you get. Okay, so let me illustrate this. This, in my view, is the hardest problem. The next one is later, only because it's more annoying to implement, I would guess, but it's not like that bad. By the way, something I should mention. This previous problem, this is a 2700. So if you want to free 2700, there you go. Paste in, just figure out small to large and then paste in the formula, and that's basically it. Although I think it shouldn't be a 2700, it should be lower. Alright, all these inputs are 4. Why would they do that? So, everything is a price and a amount of cookies it gives. So say this would give you, so this would cost 0, 2, 3, 100. And this would give you like 1, 7, 5, and 60. And now what you want to do is you want to get to like, I don't know, some number of cookies, like 1,000. So basically, you start off with the first one, or you start off with nothing, and you can buy the first one. And then, so each like, what is it? What do they call it? Each building costs a certain price, and it will give you a certain amount of cookies per second. So like, why, I said I'm on live for this 4-hour stream, but I'm losing my train of thought all the time because I'm just like, tired. It's natural. So we basically, at this, like every second we get this certain amount of cookies per second. And then so we can use our cookies to buy a new building so that we can potentially get more cookies per second in the future. And then we can use that one to buy this one. I don't know what the hell that arrow was. It was like a camel. And then we can buy this one, and then we can use this 60 per second to get to our total goal. We're interested in the minimum amount of time it takes to get to this. To get to the end. Okay, so first of all, let's do some optimizations. First, we can sort by price, because like, why not? Then what we can do is we can say that the cost, like say we have something that costs more, but has less value than something else previously. It's a triple arrow somehow. Could make a very creative arrow like this. Right, so say we have something that costs more, but gives you fewer cookies per second. Why would you do that? Don't do that, right? Like, spend less, get more. So, yeah, just like be like common sense, right? So we can remove all of the values that are we can remove all the buildings that are sort of obsolete. So like say we remove this one. So if we do this, now we have an increasing sequence of prices and an increasing sequence of costs. Because if we had ever like an inversion where we had a higher cost to a lower cost, because we sorted by prices, we have a higher price and we have a lower cost, or an equal cost. Well, equal doesn't matter, but we have a lower like amount of cookies, which is dumb. So we would get rid of that. So therefore, the prices are increasing and the cookies are increasing. I keep saying costs instead of cookies, and that's like totally wrong. It makes no sense. So the cookies are increasing and the prices are increasing at the same time. So now, much like the logging problem, the D, I believe that it was, right? Or was it E? No, it was E. Much like the logging problem, the only building that we care about is the latest one that we've bought, the last one. So, because we can only have one building at a time and everything else is useless. So, let me repeat the same words over and over again, because it's the same thing. Let dp of I be the minimum time. I can't control my mouse. You see, every time this happens, it's because I click a button on the pen. And so if I click on this, it like goes crazy. And I can't even reproduce it. What did I do? I don't know what I did, actually. I don't know what button I clicked, but I know it's some button. Alright, I'm confused. So, dpi is the minimum time to get to I. But also we may have some cookies left over, so it also stores the max cookies secondhand. Like, first we want to minimize the time, and then after that we want to maximize the cookies. And notice that these are independent of each other, because 1 unit of time less oh, you can change that? Okay, well, now I feel stupid. So you can so like 1 time less means that like the cookies are going to be like these cookies are sort of a remainder. It's going to be, the max cookies are always going to be less than the cookies you can get from using it to buy something, because otherwise if you had more, then you can skip a turn and use and then you can drop a turn and use 1 less second and still have a positive amount of cookies left. I feel like I'm overcomplicating this. I feel like there's some way to do it better, but I don't know. Perhaps not. I think that works. We store min time and max cookies separately, and we want to minimize this and then afterwards possibly maximize this. So how do we do it? Well, we care about some previous building that we used to get this one. So it is the minimum over all j being less than I, we're sorted by time, of how this works. So I'm going to let tj be the time and m of j be the amount of cookies. So these are separate values, but they're like stored together. So it's like, this is a weird recurrence, and this is why it's not so nice. We have the ceiling value of the price of I minus the amount of cookies we have initially, divided by the amount of cookies we get from j, plus t of j. That's not nice, is it? It's not that nice. And then we also somehow have to compute the time value. So we actually need the index of this too. So like, this is weird. This is a really weird recurrence. It's not good. We don't want this. So what if we did something else? What if we ask the question, what's the earliest time we get to I? Just like drop the max cookies for now. Earliest time we get to I. What's one way to check the earliest time we get to something? We don't want to actually compute the time, because that's not good, because that sort of gives us some weird that gives us some ceiling values and some like doubles and stuff like that, and it's even weirder because we still have to like account for certain things. It's not nice. What we would rather do is figure out a time point, because then we can query the convex hull for the time point and we can figure out if we have enough cookies or not, and figure out our remainder from that. So how do we get a time point? Well, we could use doubles here, actually. This is one way to go. It's not actually the worst option. So using doubles here and then just like reconstructing the answer would give you an O of log n query. But I don't want to do that. I want to use integers because we have enough time anyway, right? So why don't we just binary search on t? Makes implementation smoother. It adds an extra log to the complexity, but it makes implementation smoother. So now we have log squared of n, or something like that. Or we have like log n times log of s. So binary search on t. Then to figure out if we can get a specific t, we figure out the number of cookies we can have at t starting at all other places. So the number of cookies we get at t is, let's define this now, the maximum over j being less than I of the amount of stuff we can get from this, which is to say it's t minus dpj, because that's the amount of seconds. And in fact, if we define dpj as the earliest time we can start using I, then that's better because we need an extra second to switch. So somehow there's a +1 in here. So it's t minus dpj times the amount of cookies we get from the current j that we have. So times the amount of cookies from j. Actually, we'll call this tj because we also need the remainder. Plus the maximum remainder we have, so mj. Look at that. We have a line. Look at that. Look at that. T times cj minus t of j times cj plus mj. Write out one more just to make it clear. T times cj plus m of j minus t of j times cj. Slope, intercept, and x value. There we go. We have another convex hull. We have two separate ways of using convex hulls to solve this, which is kind of cool. One of them's faster but kind of more annoying, and the other is easier to implement. And actually, it's not the worst, because theoretically, if we use doubles and we find this time explicitly, then what we could do is we could then use this convex hull in another log n query to figure out the exact amount of cookies we get. But I think binary searching on t is just easier. And also note that like this has to be positive for it to work, otherwise it doesn't make sense, but that's fine because it is, because we can do we can like only start the binary search from the last time that we get the previous one. So we binary search on like, the time can be like dp of I minus 1 and like s plus like 50 or something. And then we can binary search on this range. And note that s plus 50, because the first one is 0. The first one, we have to have at least one with 0, and that gives us at least 1 cookie per second. So the upper bound is like s plus 1 for the time we'll take. So yeah, that's basically it. So we're binary searching on t. And that gives us these values. Then we find out the number of cookies we need. So let's do this. Scene to n. Let's just like actually do it. Read in the values, and all right, we can do like pair Then first is price, second is cost. Now sort v plus n. Then we're going to prune the ones that are g for good. We're going to prune the ones that are like irrelevant, because otherwise it gets kind of weird, the cost we have. So, because otherwise, like, we assume the last one is best, but that's not necessarily true. Although it's actually worse anyway, so it doesn't really matter if we do this, but I'm going to do it anyway. So, actually, you know what? No, it's not necessary to do that. That's just sort of overcomplicating. Because even if we make this assumption and it's wrong and we have some inversion, then it will be better to go here and not buy this anyway. So it doesn't affect our answer because it's strictly worse than what our answer will be. So that's fine. When we store pairs of DP, the first representing the time we get it and the second representing the leftover cookies. So DP of 0 is equal to make pair 1 0. We start using it at time 1. Now for I equals 1, we want to insert this line, and this line is going to be t times cj. Now this line is going to be cj and mj minus tj times cj, where tj is dpi dot first, mj is dpi dot second. So cht dot insert what is it? So the cost of j is the cookies of j is the slope, so the second value of that, and then the first is 0, so it should be dp0 dot second minus dp0 dot first times the cookies, so v0 dot first, no, dot second, right. So now, we're going to do binary search, rv equals s plus 50, just use that. 50 is totally arbitrary, it can be like 2 or something, I don't know, I'm weird. While LV is less than RV, now MV equals LV plus RV over 2. This doesn't overflow because that's at most 10 to the 16th. Well, actually, this is kind of annoying. Guess we can use int128. That's kind of a thing we can do. Should we use int128? Is there a better upper bound on the stuff we can use? We can take the largest slope. We can get a better upper bound, I guess. So it's like, say we're going to use the previous building to get this one. Then we get like dp of, that's like t of I minus 1 plus like but it's like the maximum of all of those, isn't it? No, it's like an upper bound. We could possibly do it in lower. That's like P of I over the amount of cookies we get from I minus 1. And that's an upper bound on the time we use, and it won't overflow, I think. No, maybe it will. Wait, okay. This is messy. It might just be easier to use int 128. Let's do that. Alright, so we're gonna whip out this bad boy, and we're gonna say that force that conversion to happen. C is equal to what would it be? So cht.eval. This is annoying. Eval at time mv. If C is greater than or equal to, C is greater than the price, no, if it's greater than or equal to, wait, we want the largest one that's greater than or equal to. So if it's greater than the price, go down. Vi dot first the price, then we go down, so RV equals MV. Otherwise, LV equals MV plus 1. So then for equal, we'll go how does this work? For less than or equal, we go up. Feels like equal will always be wrong. Wait, what am I thinking about here? So we want if it's less than we go up. Otherwise we go down. Oh wait, okay, that works. Yeah, okay. We want it to be equal. So then LV is the answer, and dp I equals make pair LV the time, and then the cost will be what? Or the amount of cookies we have left over is simply the cookies minus the price. Vi.f. I can see my brain shutting down at this point. Now we insert the line, which is to say we insert the cost vi.second, dpi.second minus dpi.first times vi.second. Yep. I'm using this to compute the cookies. Right, so now 1E 17. So will this be? So be dpi.first, the time plus the amount of cookies it takes. So it's S plus, so this is the amount of cookies we need, the leftover. So we're basically asking for each building, how long would it take to get the answer from this one? So it'd be dpi.f, the time it takes to get there, plus, oh, also this is +1 because we need an extra second to switch the machine. I keep saying machine instead of building. DPI.first plus the remaining cookies, and then that's ceiling divided by the production of this machine. No, wait, so this is, what is C? This should be DPI, that's second. And then that's ceiling divided by the production of this machine, which is the second value, plus VI.second minus 1, because ceiling, VI.second. I don't trust this. I think I've gotten something wrong. There's still some sort of, oh, what the hell, insert line. If you get this really long compiler, that's because you used insert, and you have to use insert line, otherwise it's going to hate you for the rest of your life. So don't do that. .first. vi.s. Oh yeah. I didn't copy the input. What am I doing? Floating point exception. That's not fun. Oh, it's because I mixed everything up, isn't it? Yes, it is. Okay. Okay, hopefully that doesn't hurt me in the future. But it probably will. Eight. Am I off by 1 in like a lot of ways? 7. Am I off by 2? No. Okay. So like there's something here. Maybe I get rid of this -1. Maybe I just get rid of this. I don't know how that works. Maybe it's like weird. Oh, maybe it's sort of convenient in the way that works. I mean, I guess. It's passing samples. It's passing samples. It means it's possibly wrong, but I don't really care. I'll look only if it's wrong, because if it's right, then it's fine. I'm currently doing problem J from this mashup that you can find in the description. All right. So this is the 2800. Look at that. That's fun. It's also a div 1e. It goes to show how not well known convex hull trick used to be. Change that back. Yeah, I mean, some of these are definitely going to be hard. Like, maybe the earlier ones are plausible. I mean, this one's just like, it's designed to just be bash out the formula and then do it. There's not much else to it. And this one also. Like, the ones I designed are bashing out the formula. This one's a very well-known DP thing. Maybe I'll link my template in this problem so that people could use it, perhaps. What IDE do I use? I'm using Notepad++ and then Cygwin, which is like Bash for Windows to compile. Notepad++ is undisputably the best, so... Dude, my mouse. Oh my god. Can't click. Like, you see what happens? I try to just drag it and then it just unclicks. Alright, this is the last problem. And it's a fun one. It's a really fun one. It's a 2900. I have technically solved it before, even recently, but it's still, like, still worth having in this. I said it isn't DP, and it's not. Even though it looks a lot like DP, it actually just, like, has nothing to do with the solution. But, that is how it goes. Okay, so here we go. Play with functions. It looks like that. So probably the hardest part about this is parsing the statement and understanding what we're actually doing. We have this function. And basically, we have this function that operates on an array. So we have a value I and a value j. I represents the current index. Actually, no, that's wrong. J represents the current index. So J can be like here, for example. And I is sort of like a counter for how many more turns we have. Because notice that no matter what you do, I goes down every time you invoke the function, and then you add aj. So it's sort of like, here's the way this works. Imagine like you're trying to optimize this process. You start at j. At the beginning of every move, you gain the array value of the cell of the location you're currently at. Then you can either stay in place or move to the next one. And then that's your next turn. And then you have, and then in this turn you gain the value that you're at. And then you can either stay in place or move to the next one. And then you keep going until you run out of turns, and you have I turns. It's also important to note that I is less than or equal to j, meaning that no matter what, like, you'll never not be able to move left, which is kind of a nice thing. But okay. So like, what does this mean, right? What's interesting about this? So, what's our optimal strategy going to be? Say we don't move. Okay. If we don't move, then it means there's nothing better on the left. Because say our current value is 7, and we have some like 12 on the left that we want to reach. And like we have some other value like 5 here. If we don't move, but we decide later that we're going to go seek out that 12, and maybe we have some other elements on the right, whatever, or on the left. If we don't move, but we decide we're going to seek out that 12 later on, then that time we didn't move and that time we stuck with the 7 would be better off instead not moving at the 12. Because here we get a free 7, but here we get a free 12. So like, take the 12. And that means that if we don't move, it basically means that we have nothing better on the left. Because if we did, we wouldn't want to settle. We would want to continue moving until we get there and then not move, so we can get more of that higher value. So we never settle and then keep moving. Meaning that we're going to the path we're going to take is we're going to move to the left up until we get to a certain value, and then we're going to stop. We're never going to not move at a certain point until we're at the end, because if we did, then that end would be better. So it's better to not move at the end. So really, our path is like this. We start at J, we pick some X, we move from J to X, then whatever turns we have left. So this takes, let's see, 1, 2, 3. So it'd be J minus X turns. Meaning we have, after doing this, we have I minus J minus X turns remaining. Or I plus X minus J. Then, what we get is this many like the remaining amount of turns, we get X. So the total value we get is, well, we get each of these values once. So imagine like prefix sums. We get the sum of the values from X plus 1 to J, meaning that in prefix sum terms, it's the prefix sum of J minus the prefix sum of X. Plus I minus X, or I plus X minus J. Wait, does that make sense? Yeah, I plus X minus J. I think that's right? Like if we move 1, then the difference between coordinates is going to be 1 or 2. Or whatever it is. So it's I plus X minus J times AX. So the answer for a query, again, this is not DP. It's just sort of the same sort of thing, like a culmination of everything we've done so far. So the answer for a query is the value, we have the prefix sum of J minus the prefix sum of X. Or sorry, it's the maximum over a range. And what is this range? It's the range of the X's that we can reach. So if we have 3 moves, for example, we can go here and then here and then here. And we can reach anywhere between J minus X and J. Note that we actually get 0 from this, meaning that it's pointless, but like still. Or actually, it's not J minus X. It's J minus the number of turns we have, meaning it's J minus I. So that's cool. Yeah. So we get J minus I. That's right? Like we can move 1. That kind of makes things messy. I guess we can assume that because we're 0 indexing, it kind of makes things messy. But what we can assume instead is that we're like, we can't make this last move because, like, if I is 3, we can only get 3 values at most. I mean, that even if we make this move, it's like pointless. There's no reason to make this move because it won't give us anything. So we can assume that we can only reach these 3 and not the last one. So J minus I plus 1 to J. That's the range of values we can reach when we move. That being said, of the x's we can choose, now we have this constraint for it. So It's within the range of values that we could possibly reach. So x being between these values. No, it's not dp. It's just like, it's similar. It's the same sort of convex hull trick that we're doing, so I wanted to include it. It's just like a bonus problem, kind of. So maximum on this range of the cost function. So p of j minus p of x plus the amount we get, which is I minus x, no, I plus x minus j times ax. We're going to do the same trick that we've done for so long. J minus I plus 1 between x and j, where we get, in fact, we can move the pj out because we're fixing x. So j is constant. So p of j plus how does this go? So we get I minus j times ax plus x times ax minus p of x. If we bracket these together, then we can group everything like we always do. We have a slope, we have an intercept, and we have a x value. Well, PewDiePie has a new diss track? Alright, I gotta watch that after then. Nice. So notice this is querying a convex hull as always, except now we have a range for it. How cool is that? That we have a range on a convex hull. We have a range query on a convex hull. This is why I kept putting off building a segment tree on convex hulls, because this problem requires it. You need a segment tree with a convex hull in each node. So, luckily we've bashed out the formula. So the rest of it is just to implement the segment tree. If you guys want to watch the diss track, that's fine. Like, this is not going to be interesting. This is just stuff. You know. So, let's see. What we're going to do is not do merging at all. And so we're going to get rid of, like, everything. Right. So we're just going to use this. Actually, I'm not even going to use this. What we're going to do is we're going to, I should put this above then. If I can copy successfully. So we don't have lazy propagation, we don't have any sort of updates. So we can get rid of update entirely. That's cool. And we're just going to modify the segment tree to work for this. So this is negative 1E18. We're going to modify this for LL. And this is going to be simply tree I dot eval it's going to like just modify everything. That's how it works. Make everything work for this value. I'm going to eval at x. I'm going to take the maximum over all of these. Actually, this should be the minimum. So I guess like that, and then like that. So the slope we insert is negative ax. and then negative x times ax minus p of x. Yep. And we can get rid of like everything because we're just going to build the hull naively. So tree I dot insert. What do we want? We want a line with the value negative aj, negative j times aj minus pj. I need that bracket there. Yeah, and then we define the prefix sums. Should we want to move this up so that we can like finish this off? Yeah, and then we can do prefix sums over this array. 10 to the 5th. I'm going to do prefix sums. Do this whole thing in one array. R equals 0. Cn to ai. R plus equals ai. Pi is equal to r. So let me use p here. And that works. Hopefully I got my formulas right. So now we ask for the queries. So Cn to q. LXY. Cn to x to y minus y. So then the answer we get is prefix sum of j, py plus don't need that. st.query. So the range we want is y minus x plus 1 and y dot val. See if that works, I guess. Okay, that's... I don't know what that is. What are we doing? Oh wait, this should be huge. Oh wait, and the value we want is x minus y. Okay, that's a lot of compile errors. What the hell? I don't need that. Don't need that either, because this is a long, confusing my own template now. What is this for? Hello. Does this work? Finally. Now we can get the wrong answer. 12995. Okay, I guess it is possibly correct. Let's find out. So once again, we explicitly define the formula, and then once we do that, the code is like crazy easy. Even despite it being a segment tree on convex holes, the code is like quite simple. We just like plug in the formula that we already derived, and then we don't have to do any thinking during the code. But indeed seems like it works. 701 milliseconds. The time limit for this is a second, so I also raised that myself because I didn't want to make it too harsh. Anyway, if you guys are interested in that one, that's a 2900. So if you're interested in some free high difficulty problems, here you go. I've already gone over them. So there we go. Chain of ors is in the chat. If you guys really want, I can get rid of features demoralizer too, because I think he's gone. Reactive PDF. I don't have any reaction left in me. These are. I'm tired. Yeah, it's been what, 5 hours now. Are my streams like this where I make a contest and solve? Yes. Pretty much. Yeah. These are all the topic streams. So, like, I have many of these. You can see I have a playlist here where also I've done some more basic DP ones. And then this is, oh yeah, Code Rams is going on right now, so if you're interested in that, that's possible. Yeah, like I have a bunch of these, and all of these mashups are included with the streams. Yeah, all of these are in this playlist you can click on, I think. Link should work. And then the mashups will be in their respective descriptions and stuff. Alright, that's it. Any other questions? Any other things? Code Rams is a contest that I tested, and it's kind of cool. Kind of interested to see how people are doing. Oh my god, Maxim is doing it? Okay, well, he's just gonna win. Surprised that he doesn't have 9 yet. Alright, so that's not even a contest. You have an LGM doing a contest in the next, yeah. Nice. Okay, that should be funny. Man, when do we get more viewers as the stream is ending? Alright, well, I have nothing more. So that is, yeah, if you want to ask a few questions, I can do that for a bit. And I might just like collapse or something. Practicing for stuff like ICPC, this is good because ICPC is 5 hours. I am in high school. I have not participated in IOI. In fact, I'm not even sure if I'll do it this year. So, yeah, it's over. It just ended. Like, I just did the last problem. If you want to talk to me more, actually, you can talk to me in the Discord, which is also here. Give a tip for a problem. Yeah, join my Discord and then talk to me there. This is in the description, so that should be good. Yeah, I'll leave it at that. If you want to talk to me more, you can join that. 5 hours and 14 minutes. Okay. All right, I'll be gone. See you guys. Have fun with life.